And now we're finally live. What's up, everybody? Welcome back to camp. Thank you so much for everybody that's watching in real time right now. Today is, what is it, like the 7th or something? Some people say these aren't live, but they are live. Today's the 6th. We're in the future, actually. That's how live we are. Drop some just campfires in the chat, maybe get some tents going. A couple updates really quick. I have this beautiful shelf behind me. I'm eventually going to get a P.O. box set up. If anyone wants to send anything that's going to fit into this beautiful peyote experience that we have here, I would love to see what you guys have to send. For now, we just have a beautiful crafted parrot. Also, just let's get an F Miles in the chat, because Miles just is the worst, as always. So if we can just keep that going. Miles is a dear friend from college that people don't seem to like, which is totally fine, okay, because we believe in free speech. Today, I have a very, very special guest, someone I'm extremely excited to speak with. He's brilliant. He's on the forefront of exoplanet and exomoon research. He's very handsome. He's David Kipping. How are you, sir?
That's a very generous introduction. Too generous, thank you.
Absolutely. Dr. David Kipping.
That's fine with me. I don't really care about the title. Some people get worked up about that. I'm like, whatever.
You went to school for too long to not be called doctor.
Yeah, I think when you first get your PhD, it's a big deal. You want to change your credit cards and your driver's license. And then a few years later, you're like, actually, I don't want people to think I'm a doctor on an airplane. That's maybe not advantageous.
You're on an airplane. They're like, is there a doctor here? And you're like, look, when the wobble of Jupiter. And you're like, okay, this is not what we need.
This is not the right doctor.
Okay. Not only are you a doctor, but you're also, more importantly, a YouTuber.
Yeah, CoolWorlds. Yeah, I got my t-shirt on today, my CoolWorlds t-shirt.
Brilliant. Yeah, CoolWorlds is an amazing YouTube channel. If anyone doesn't know about it, shame on them. It's a brilliant channel and almost at 1 million subscribers. I've noticed that.
Closing in.
Yeah.
It's been a long haul to get to that point. I've been doing this for 8 years at this point, but we're getting there. We're getting there.
Well, it's an amazing channel, and you are effectively putting out extremely interesting science content for a general audience. At least I can understand it, so it's general enough for my dumbass.
It's working.
But it's absolutely amazing, and if anyone's interested, they should absolutely look at it. It's called CoolWorlds.
Yeah.
Can you explain why it's called that?
Yeah, it's just named after my group. I think a lot of people assume that it means like cool as in hip, like hip worlds or something.
Trendy worlds.
Yeah, trendy worlds. But that's not really what we're going for. I got inspired because there was another research group in San Diego called the Cool Stars Group. And so there are some stars which are very hot and some which are cooler. And I think the cool stars actually are kind of the most interesting stars. These are like these diminutive red dwarf stars. And about 75%, 3/4 of all stars in the universe are stars like that. It's cooler than our own sun, which I think is amazing. Like, we live around an unusual star. Most stars are way cooler, way smaller than our own sun. So I loved the name Cool Stars, and I loved the topic. And in the same sense, when I was starting my group, I was like, what kind of planets do I want my team to focus on? And for me, the planets which are far away from their stars,
Now, Earth would technically be considered a cool world.
Yeah, by my definition.
Okay.
Yeah, for sure. There isn't like a strict scientific definition of like, you can look up in the dictionary and CoolWorlds, it has like a strict, like it has to be in this separation, I think.
Yeah.
It's, we're using it fairly colloquially, yeah.
Right. It's objectively a relative term.
Yeah.
Cooler than. You know what I mean? You're like, all right.
In all sense of the word, Earth is a cool world. I'd say once a planet like Venus is maybe, even then, that's still probably cooler than most exoplanets we've discovered. It's kind of surprising that most of the exoplanets, we know about 5,000 right now. You look at about the top 3,000 of those, they're all something like 2,000 Kelvin in temperature. Super, super hot. They're all very close to the star. And it's not because the universe only makes planets close to the star. It's just because our detection methods find it way, way easier to find those. So we know of loads and loads of super hot planets, and the cool worlds, they're much harder to find. We only know of like a few dozen planets at separations like the Earth from the sun. But for me, that few dozen sample is the really precious, special bunch that we want to focus all of our attention on. So that's kind of what we put our efforts on.
Right. And it might be helpful for the conversation just to get like a little word bank going as we go forward. Can you just define for the audience what an exoplanet is?
Sure. It's pretty simple. An exoplanet is simply a planet, just like the planets in our own solar system, but it's going around another star, not the sun. So you might actually call the planets in the solar system, if you're being really technical, endoplanets. Exo means outside planets. It's shortened from extrasolar, so outside the solar system planets is really what it means. And so, yeah, if we're being really technical about it, we should probably call the planets in the solar system endoplanets because they're inside the solar system. Nobody's going to call it that. So normally when you hear this word planets, we're probably referring to planets which are inside the solar system, and exoplanets are planets which are light years away. So these are, the nearest star to us is Proxima Centauri. It is 4.2 light years away. So it takes light itself over 4 years to travel that distance. But of course, many of the exoplanets we're discovering are thousands of light years away. They're all inside the galaxy. We haven't found any planets outside the galaxy yet. We're hoping to do that. They should be out there. Obviously, they're very distant, so it's challenging. But the 5,000, 6,000-ish planets that we know about, they're all within sort of 1,000 to 2,000 light years typically.
And what is the issue with identifying cool planets versus hot planets? Why is it so much harder to do this work?
Yeah, there's a couple of really successful methods for finding planets. There's many methods, but the two dominant methods, one is called the transit method, which is looking at eclipses. So we had an eclipse in the US last year, was it? I think I went to see it down in Texas.
You were there?
Yeah.
Were you in Austin?
I wasn't in Austin. I was in between. I was kind of in the middle of nowhere, but I was in the path of totality. It was this weird like Christian camp. Actually, I got invited to go there, and I was kind of apprehensive about it because I was like, "What's going to happen at this camp?"
The rapture. Jesus is going to come back, take everyone.
Like, it seemed a little bit spooky. But the guy was brilliant. He was so kind and nice, invited me over, and he had a bunch of amateur astronomers, and it was in the path of totality. So everybody just camped out. They all had their telescopes set up. And we saw this beautiful eclipse as the moon passed in front of the sun. And that's the same method we use to detect exoplanets. Now, it's not a total eclipse because we're so far away. I mean, think about the moon. The moon is really small compared to the sun. The only reason it looks like a total eclipse to us is because we're parked so close to the moon. So just perspective gives it that totality. But if you're really far away, then it's just a tiny dot in front of the sun. And so those dots, as they pass in front, they will block out a tiny fraction of light. And we're talking less than 1%, sometimes even parts per million fractions of light that they block out. So it's kind of the equivalent to like a tiny fly flying in front of floodlights at a stadium or something, right? So that's the amount of light that gets blocked out. But with our very sensitive cameras and telescopes, we can detect that tiny dip. And if it repeats, every time the planet passes in front of the star, it will come round, go in its orbit, and come round again. It will do another dip and another dip. And the timing between those dips is the year of that planet. In other words, its orbital period. So we can figure out from that basically how far away the planet is from the star.
Is that cool planets or is that all planets?
All planets that transit their star. If it passes in front of the star, we can use this technique. And the amount of light it blocks out is obviously proportional to how big it is. The bigger the planet is, the more light it blocks out. So we can figure out how big it is, not how heavy it is. That's different. Just how big it is. So it could be, a Jupiter-sized planet, but actually maybe only the mass of 10 times the mass of the Earth, which would be incredibly puffy. So actually, we found planets like that. We call them styrofoam planets.
Oh, really?
They have densities akin to like candy floss. And it's bizarre. Like nobody expected to see planets that were that puffy, that light. It's almost like, how does gravity even hold this thing together? It's so tenuous. And yet we find dozens of those things in our data. So that's a very powerful technique.
Do the moons and stars of these planets, if they have them, are they equally as styrofoamic?
The moons, we don't know. We do often see in these systems, it's not unusual to see multiple planets, and sometimes you do see that multiple of the planets are also puffy. So there's entire systems filled, we call them super puffs. So there's these systems that are filled with super puffs. Yeah, we have kind of fun names.
Sounds delicious.
Yeah, it kind of makes you almost hungry for some kind of floss or something, yeah. So these planets are kind of unusual, not expected. And there are, on the other hand, planets which are overly dense. They're like cannonballs. They're just like, they're very, very small, maybe like twice the size of the Earth, but 10, 20 times heavier than the Earth. And so when you look at, okay, what must that thing be made out of? It's like a pure ball of iron, like a cannonball, literally in space. And again, nobody really expected to find too many of those things. So when we look at exoplanets using the transit method, we get their sizes, we get their periods, and then to get the masses, which I keep alluding to, we have the masses as well, we do a different technique, and that's to look at the wobble of the star. So when you talk about mass, you have to go through gravity. Gravity and mass is that's the only way that really mass feels itself is through gravity. So the gravity of the planet will tug on the star. So we often have this picture that a planet orbits a star. And that's true in one reference frame, the reference frame of the star's perspective. But from the planet's perspective, it's the star which goes around the planet. And that's why, if you go back to Ptolemy's time, we thought that that the Earth was the center of the universe because it seems like the sun goes around.
As a Catholic, I still support geocentrism.
Yeah,
okay? I'm like, look, the church is right.
Keeping that flag going.
Very traditional. Okay,
yeah, it's a narrow view, but there's some view out there. And then another perspective, which is kind of the physics perspective, is that there's actually both of them are going around each other, and there's a center of mass between them. So kind of like a seesaw, there's a pivot point between those two, and truly. They are both going around this common center of mass, the center of gravity.
Creating like a helix, perhaps.
Yeah. So when we look at these stars, we see them wobble. Sometimes they're moving towards us, sometimes they're moving away from us. And when they're moving towards us, the light gets blue shifted. So this is the same effect like an ambulance siren coming down the street, that the siren goes up in pitch as it comes towards you. And as it goes past you, it's moving away from you, the pitch goes down, it gets more bassy. And so that same sound effect also happens for stars' light. And so the star appears bluer just a tiny bit when it's coming towards us and redder when it's moving away. And so you look at these stars and they're going blue, red, blue, red, blue, red, blue, red. And the period of that wobble in space tells us again the period of the planet, and the amplitude, how much it's moving back and forth, tells us how heavy the planet is around it. So using that combination of techniques, the wobble of the star gives us the mass, and the transits, when they pass in front, gives us the size. And so once we've got the size and the mass, we can actually figure out things like, is it styrofoam or is it a cannonball? We can get essentially the density, how bulk heavy is it?
Wow. Now, there's a logistical issue with doing this as well, right? Because these planets are so far away. Even just getting telescope time to observe these planets is like impossible. It seems like
it can be hard, but in another sense, it can be easy. Actually, the transit method has a lot of data, and so of the thousands of planets that have been discovered, the vast majority were discovered that way. And the way we often use this, there's a couple of missions. One in particular that was super famous, called Kepler, named after Johannes Kepler, who is a famous German astronomer who came up with Kepler's laws. This telescope was launched by NASA, I think it was 2003, and it went for about 4 or 5 years before it had some issues on board the spacecraft that meant it couldn't observe the same patch of the sky anymore. But for 4 years, it stared at one patch of the sky continuously, and every 30 minutes it took a photo of about 200,000 stars. 200,000 stars, it took a photo of them every 30 minutes. And from those little photos of every single star, it was able to calculate how bright the star was in each image, and then you can make a time series. So in each of those 30-minute chunks, you look at how bright the star is, and you see, did it get dimmer in time for a short interval. So for 200,000 stars, you do this, and the probability of getting an eclipse is about 1%. And so you might expect to find from 200,000 stars something like 2,000 planets. We actually found more than that. We found 4,000, 5,000 planets from Kepler. And the reason was because there isn't just one planet around those stars. It's kind of startling, but every single star has, on average, at least one planet. And in fact, often many more than that. And again, that seems obvious looking at the solar system. That, okay, look, yeah, the solar system has 8 planets, so surely everywhere has a whole bunch of planets. But before Kepler and before exoplanets as a field started, we really didn't know. I mean, maybe it was possible that stars very rarely have planets. And the reason why we live in a system that has planets is because, of course, we have to. Like, there's no, life has to begin on a planet. So, of course, we live in a solar system that has planets, but maybe the vast majority of stars are empty. That was perfectly possible. Mm-hmm. And indeed, there was lots of theories and calculations that really struggled to make planets on the computer. Like when you tried to simulate the gas and the dust, they just didn't seem to make planets. So there was a real concern that maybe we wouldn't find that much. And so Kepler kind of turned that whole thing over and said, no, like they're everywhere. And if anything, that's kind of given us a major problem with thinking about why aren't there aliens out there, right? Because that was one possible solution. One possible solution would be planets are just rare. Or maybe Earth-like planets are rare. But as far as we can tell, neither of those are true. And so with 100 billion stars, at least, in our Milky Way, and we know that on average, all of them have planets, it really raises some very fundamental and profound questions about how come we don't see anything out there? Like, what's going on?
The old Fermi paradox.
Yeah.
Yeah. It is an interesting... The light element is the thing with measurement that I find very striking. So I'm curious, when measuring, because again, we're dealing with, millions of light years, or potentially
thousands of light years typically for the exoplanets.
So these things we're seeing the light over a period of time, which again, now it's like kind of in the relativity world. But you're basically looking at stars and planets in the past.
Yeah.
But how can you trust that there's a constant sort of light movement? Because isn't it possible for light to move slower? Like, is it because all things are equal in terms of the movement of light that you can trust that what you're seeing is actually what it is? Or does there become a measurement issue with the speed of light and time when measuring these exoplanets?
In a vacuum, light will always travel at the same speed, which is the speed of light in a vacuum. So that's about 3 times 10 to the 8 meters per second. So we don't expect in a vacuum there to be any differences. The path of light, even in a vacuum, could travel not in a straight line though. So light doesn't actually, we think of light traveling in a straight line, but really it travels on geodesics, which is to say it travels in a straight line in the curved space-time that gravitational masses impart. So if I had, and we see this effect, this is one of the main evidences for dark matter. If you have a very distant light source, let's say it was like a supernova or something very bright, very far away, the light that's being emitted could be traveling millions of light years. And so it is quite possible that something will just get in the way, like photobomb it, basically. And dark matter in particular can often do that. And light can travel through dark matter. It's basically invisible matter. So it doesn't block the light. It will just pass straight through it. But because it's mass, it will act like a lens and it will curve the path of light. This was first seen by Arthur Eddington in another eclipse. It was a total solar eclipse, and he looked at the positions of stars very close to the sun before a solar eclipse, and then he measured them when the stars were basically far away from the sun, and then as the Earth rotated around, the stars' positions change, and then he measured them again during a total solar eclipse. So you had to use the total solar eclipse because otherwise the sun is too bright and you wouldn't be able to see the stars around the sun because it'd be blasted out by the contrast. And he noticed that stars shifted position to where they should be, and so that shift was because it proved that the sun was bending light around it into this curved path. The same way dark matter can do that. So if light takes this curved path, it will therefore take a little bit longer to reach us. However, it's a pretty small curvature. So, if something's 4 light years away and there's a gravitational mass in the way, it might, modify it by a fraction of a percent or something.
Okay.
That's not going to be major. The other way you could slow down light would be having normal matter in the way, which would cause extinction, which is to say it would get dimmer. So if you have just a cloud of dust in the way, the same dust that you would vacuum up off the floor and just put it inside, which is a lot of that kind of stuff floating around in space, that will absorb some of the light, so it will make the star appear dimmer. It will also make it appear redder in general because dust tends to prefer to absorb blue light over red light. So you get that kind of color change and dimming of the star. But also whenever light travels through a medium, like water, if you shine light through water, it will travel slower. So the speed of light in a vacuum is not the same as the speed of light traveling through any kind of medium. It will always travel slower through a medium. So therefore, there'll be another slight change in the speed then. And so there has been some experiments where they've been able to sort of play around with these metamaterials, which are kind of like artificially nano-manufactured materials. And this is not my expertise, but they have some very impressive experiments where they can slow down light to centimeters per second. And so you can actually see like a beam of light traveling through an object, even actually temporarily freezing it in some cases. So that's not going to happen in space because these are like very controlled lab conditions to pull that off. Interesting. But yeah, you can manipulate the speed of light by using materials.
Is that through density of the material that it moves through?
Yeah. And kind of the structure of that material, and the use of exotic matter like Bose-Einstein condensates and these quantum states can trap light into these very slow paths for a short time. So those experiments are pretty fun. But of course, when we look out to the universe, we don't think any of that's really going on. We don't see the evidence for exotic materials out there, at least large masses of exotic materials. So we tend to assume that the distance to an object is pretty much how long it took the light. But it is still amazing. You look at a star that's 1,000 light years away, that star might not be there anymore. I mean, it probably is, because stars generally don't disappear in that timescale. But who knows? A civilization could have arisen in that 1,000 years. They could have built a shell around the star, and the star might be there, but now it might be completely masked from us, and we wouldn't know.
Interesting. Yeah. So I guess, in other words, the movement of the light, even if it is slightly bending, it's not enough to effectively change the calculation about what that star or exoplanet is doing. Is that fair to say?
Yeah, I mean, the bending. I can't think of a star, because typically you get this bending when stars are really far away, because the further away it is, the more likely it is that you're going to get a big clump of stuff like dark matter get in the way. So I'm not aware of any exoplanet hosting stars for which that effect has ever been observed. But this effect has been seen. I mean, some of the first JWST images that we got, and certainly there's many beautiful Hubble images of this, you see galaxies warped. And that's because of the bending. So instead of getting this nice, crisp, clear disk-like galaxy, they get kind of smeared out into these kind of curved shapes. And even sometimes you get mirror images of them. So that's something famous called the Einstein cross. Maybe we could bring it up, the Einstein cross, and you can see the kind of a duplication of starlight being mirrored over onto other sides. So it's kind of like going into like the Funhouse Hall of Mirrors. Yeah, so you can see here. So that's actually just the same object 4 times.
Oh, really?
That's not. So when you first, I mean, it was kind of startling when you first see these things, because people were looking at them thinking, those 4 objects there, they seem to have exactly the same spectrum, exactly the same kind of light properties. That's pretty coincidental, until we actually realize, actually, it is the same object. The universe is cloning this object through gravitational lensing. So it's unusual to get 4 like this. That's why this is kind of a famous case, the Einstein cross. But very often you get 2. You can see in this case, you get this kind of like blurring around. So in this central region here, that's why we know in that region there must be a whole bunch of dark matter that's lensing that stuff.
Oh, wow. And so what is the actual original here? Like, what is the mold that these other ones are being? Is it the center one that is the actual?
No, I think the center one is a different object. I think what's happening here is there's an object behind it, and it's being warped around. So there's 4 light paths. So there's one object kind of hidden in the background, and the light is taking 4 different unique paths.
I see.
Around this dark matter mass to reach us.
I guess
this is kind of like trying to illustrate the lensing a little bit here. It is hard to visualize.
I see. Yeah, Chrysos. There's a bottom one here that kind of shows like a diagram that you'll see almost. Yeah, exactly, that one. That I think would be good for the audience to see. This makes a lot of sense.
Yeah.
Okay, so you have obviously the Earth here on the right, and then is this red thing, would that be that dark matter that's moving around?
Yeah, so actually in this case, you can see it's a galaxy. But galaxies always have a whole bunch of dark matter around them. So we call this the halo. So the galaxy itself probably isn't heavy enough to lens the light, but all the dark matter around it is doing so. Of course, if there was no dark matter, it'd be pretty difficult, not only because the gravity would be so much less, but also the light would have to almost travel through the galaxy, in which case it's going to get blocked out by all the stuff in the galaxy. So dark matter has the nice property of being transparent, so light can travel through it, but also bending. So that's why you get these very strong lenses like this.
I mean, it just seems like an impossible task. Like, you're dealing with light from so far away, and light can be tricky, I guess. Like, I mean, you've just given all these examples of how light can bend and change. I've heard it put into almost like the metaphor of like a Roomba.
Yeah.
Like, you have a Roomba in your home, and let's say it goes, like of 1 foot per second. And so it can go 10 feet in 10 seconds, and that is the fastest it can go. But it could also kind of go forward and then go to the side and then bounce off a wall, and it could take longer.
Yeah, it's like the traveling salesman problem is a classic problem in math, where you kind of ask, well, okay, the postman or the salesman could just go from A to B, but there's so many different routes, and you have to kind of calculate like the optimal route that the object takes. Yeah.
So I guess that is like the question that I have is like, how do we verify? Like, how do you and your team verify that the light that you're getting is what you think that it is? If it's, is it redshifting or is it moving through dust? Like, is it... So
if it's, they have different effects on light. So if it's purely being gravitationally redshifted, maybe we should talk about the spectrum of an object to give some sense here. So all luminous objects, you are luminous a little bit. You're producing some heat that's coming off you.
It's very sweet. I really appreciate you saying that.
Stars, planets, even probably this table is a little bit luminous. They all produce a little bit of heat and light coming off them. And so you could ask how much light does it produce at every wavelength, which is another way of saying like color of light. So you can ask how much light does it produce at one particular frequency of light, and the next frequency, and the next frequency, and the next frequency. And you build that up, and that's called a spectrum. Basically, every material has a unique spectrum. So if you take wood and shine a light in it, it will produce a unique fingerprint of what that light looks like. Now, for stars, they're pretty actually simple objects. They're mostly hydrogen and helium. There's a few heavy elements mixed into the atmosphere, and those produce these characteristic fingerprints of what a star's spectrum should look like. And so when we see something that's been gravitationally redshifted, or just relativistically redshifted, because it could be moving away from us, what you'll notice is that you get that same fingerprint, that characteristic fingerprint that we see all the time, but it's just shifted over to the left or to the right. In other words, the spectrum appears a little bit redder, literally, because it's been moved over in wavelength to a lower wavelength. And so that shift of the fingerprint we expect versus the fingerprint we get, the difference between them tells us essentially how fast the object is moving away from us, if it's due to relativistic motion, or if it was in a gravitational well, it would tell us how deep the gravitational well is. Whereas if it was dust would not shift the spectrum like that. Instead, it would just suppress certain parts of the spectrum. So, think about why during a sunset, the sun appears really red. Doesn't appear as... It's missing the blue light, essentially. A lot of that blue light is gone. And that's because the Earth's atmosphere is a medium, and it scatters away, it absorbs away a lot of the blue light. And so you're just left with a red. So it's the same spectrum of the sun. If you took the spectrum, it would look the same, except for all the stuff towards the blue end of the spectrum would be suppressed. It would be pushed down, and the red stuff would be mostly still intact.
Pollution is the same way, right? Like you look at the sun during, in any polluted area, and it's very orange and red. Yeah. And again, it's the same principle.
That stuff, especially if you're in, if you're like in Shanghai or something, like a city with loads of smog, all of those particles in the atmosphere will do the same thing. They'll preferentially scatter blue light over red light. So you actually get some kind of impressive, reddening of the star in those cases. So that same effect we can use, and we can measure that for starlight and for galaxies, and that helps us to distinguish what's really going on. So the spectrum is very, very powerful for that distinction.
That makes sense. I see. So redshifting is a proper spectrum movement.
Yeah, the whole thing.
I see.
Over. And that's what we do when we look for the exoplanets. That's what we're looking for. With this wobbling star method, we're looking for that spectrum shifting all the way over from one side to the other. And, these shifts, they're very small. I mean, for the Earth wobbling the sun, it causes I think the number is about 4 to 5 centimeters per second that it causes the sun to move by, which is like a snail pace. Right? So if you put a snail on this desk and make it walk across, slime across the table, that speed is the speed at which the Earth perturbs the speed of the sun. So it's so tiny you'd think it's ridiculous that we could see it. And indeed, when you look at the spectrum, it moves by way less than a pixel. So we basically take these cameras and we spread the light through basically a prism, spreads the light out into all of the rainbow of colors, and then we have a camera which captures that light. And these cameras are like your 25 megapixel cameras, like the very high density pixel cameras. And despite having so many pixels, the light itself is moving by way less than a pixel. overall. And so you'd think that was impossible to detect. Even though it moves by a fraction of a pixel, we still can detect that because it causes just a very slight change to the amount of light which each pixel receives in total. And so using this, we're able to detect things which move by sometimes just a few atoms. So if you actually look inside the pixel itself, it's made out of silicon dioxide and other semiconductor material. And the actual amount that the light moves by is of order of like a few dozens of atoms that it's shifting by.
It's like and the quark of a pixel. Right. Breaking it down.
I know, and we can still detect it even with that. So I think it's just an amazing testament to the skill of these spectrographic observers who are able to pull out this tiny, tiny signal.
Oh, wow. So it's that fine that you're able to actually see the sub-pixels of movement.
Yeah.
And this might be jumping the gun, and this might be a completely separate convo, which we can maybe visit in a little bit, but I imagine AI as a disruptive force throughout the world already, and then on the horizon of what's to come with artificial intelligence. As far as a detecting mechanism and sort of like data analysis tool, I imagine for this type of work it would be instrumental. Is it already being used, and what do you think the future application is?
Oh yeah, it's being used for sure in all sorts of fields of astronomy, including this. It's exploding. In fact, when you look at the new papers which are released every day, almost like half of them are using AI in some way these days. So it's unclear if this is we're sort of in the explosion period and it will calm down, or if this is going to be the new paradigm, that astronomy becomes almost an extension of machine learning techniques, of just using them in a different venue. One of the ways, in the wobbling case, this is so useful. I mean, machine learning is really useful when you have very, very difficult and complicated signals and you're trying to back them out. Now, if you're measuring the sun wobbling at centimeters per second, the problem is that the sun is not a perfect light bulb. It has features on it. So it has sunspots. It has things called faculae, which are like these dark, stretched out patches on the surface. And if you zoom right in, maybe you can actually find an image here, like sun granulation would be a good one to look for. Mm-hmm. You can see these little, here we go, like these little granulated patches on the surface. And so what's happening is that there's little regions where there's upflows, and there it's brighter. And then there's other regions, kind of like, convection happening in your water tank and your heater at home. Mm-hmm. The water rises up through convection, and then it reaches the top, it kind of moves to the side and it flows back down. And the areas where it flows back down, it gets cooler. And so you get darker spots. And where it's coming up, it's hotter because it's material that's just risen. So that's brighter. And so you get this, this kind of micro behavior on the surface of the sun, even though each one of those patches is like the size of the Earth or something, like huge sizes. But each one of those patches is constantly bubbling. So it's really like looking at, the surface of bubbling water. And the surface of bubbling water is not still. It's not a still lake. There is movement happening constantly. And so when you have the ability to measure motion at centimeters per second, you will see a whole bunch of crap happening on the surface of that star. And so when we take these measurements at this level of precision, no star, even if it has no planets, even if there's no planets there whatsoever, the velocity of that star will still seem to be bouncing up and down like crazy, just because the surface is bubbling so much. And so one of the challenges we have now is figuring out, when we see these weird bubbling things, is that because there's a planet there, or is that because it's the star just doing its thing?
How do you control for that? Do you have to take each ripple relative to itself to assure that it's not an actual wobble, but just a, I guess, what do you call these uprisings?
Like granulation. So, I mean, there's also, this is convection cells basically happening.
So how do you control for, like, again, this concept of this static ball, like literally not motionless, but like almost like a static electricity, like these, ripples coming off of it, trying to measure if it's moving or not seems impossible.
I mean, you raise the question that I think hundreds of astronomers are currently wrestling with. And this is right at the bleeding edge of what exoplanet astronomers are trying to figure out. We do not have a solution to this problem. We still are getting confused, and there's been many exoplanets that have been claimed, even sometimes with headlines. And you've probably read about first Earth-like planet detected, like Gliese 581G, I think was a famous example of this, where this was like 10 years ago. They claimed, okay, we found the first ever Earth-like planet. It was in the news. Yeah, you can grab this. It's Gliese. Close enough. And then 581.
Yeah, the second one there.
But yeah, I think it was planet G, not C. But there was you got it there. But this was claimed to be an Earth-like planet in the habitable zone of its star, and then it turned out later it was just the bubbling of the star. It wasn't a real planet. It was that bubbling motion that was tricking us and thinking. And so there's been many, and it must be frustrating for those at home listening to this. And I think it's true of science in general. My dad says this to me all the time. He's kind of always frustrated with science. He said, I read in the newspaper, tomatoes are good for me. And then the next day it says tomatoes are bad for me. I can't trust science.
Yeah.
And similarly, it must be frustrating with the planets, because there has been many cases where an Earth-like planet has been claimed, just like this one. And then within 2 weeks, this thing was ripped up, actually. It happened very, very fast. And it must be frustrating to read those headlines and think there's a certainty to it. And yet it gets destroyed in 2 weeks later. But I think I would try to argue, this is actually the strength of science, that science is willing to challenge itself in a way that religious doctrine is not.
It's non-dogmatic.
If something's in the Bible, you can't question it, right? That's there. It's in the fundamental doctrine of your religion. But in science, everything is up for grabs. And it doesn't matter if the person who claimed that planet was the most famous scientist, Albert Einstein, Richard Feynman, like a superstar scientist. It doesn't matter who it was. A grad student, an undergrad, even a listener to this podcast could come up with an argument as to why it's not there, publish it, get it peer reviewed, and prove that it's not real. And that's how science works. It would be discredited. So I think that's the power of science. And when you're looking at things right on the bleeding edge, like this is like, really pushing these telescopes to the very edge of what they can do, where not only are you pushing, seeing things at, tens of atoms moving across in terms of the wobbles, which is hard enough, but then you're competing with the bubbling motion of the star that we don't even understand, then of course there will be missteps. That's part of science. We're learning, the astronomers, me, you, we're learning how to do this as we go. And so we're trying to push the envelope as hard as we can, but sometimes we will make mistakes.
It is annoying, though. I mean, I grew a very close attachment to Pluto.
Pluto, yeah.
Well,
Pluto's still there, but it's still, that's still a real object.
You guys got rid of it. That's what you guys kicked it out, and you were like, you can't be here anymore. So it blew up or something. You guys just destroyed it. It just doesn't exist.
There is still Pluto is still there. It's just that what we call it is no longer a planet.
That was Dr. Pluto for years, and you guys demoted it to like an intern.
Well, not me. I wasn't. This was before my time.
See,
so
you distanced yourself. You and all your astronomer buddies colluded against Pluto, and you're like, oh no, it wasn't me.
Yeah, I mean, Pluto was a whole interesting, and people have very strong, like Pluto will always be this whole like T-shirts you can get with all that kind of stuff on it. I just don't really care that much about that because it's just what we call it. Like Pluto does not care what we call it. We can call Pluto a crap planet, we can call it a dwarf planet, whatever the hell you want. It's still there and it's still interesting. And in that case, nobody's questioning the reality of the object. I mean, we flew a goddamn spacecraft right by it and took all these beautiful photos, the New Horizons spacecraft. And if you look at some of those images, maybe you can grab some up. New Horizons, Pluto images, you can see mountain ranges, you can see an atmosphere, you can see ice shelves and glaciers and all this complex geology. And so whatever you think about Pluto, it is a really interesting, rich geophysical world. Mm-hmm. It's like, call a rose by any other name, it still smells as sweet. I don't really care what you call it. It's there, and it's an interesting thing to study. Yeah,
I guess it is an interesting point to underscore that things may be... I think the common person, myself, gets wrapped up in sort of the law of names and sort of
because it's easy to understand.
Yeah. But like you mentioned, science, there's a malleability, and that things can sort of be flexed. I had another question regarding sort of the granulation of these planets and the difficulty of actually detecting whether there's a wobble or not. When we looked at this, we were looking at the sun, I believe, the sun's granulation.
Yeah.
Which is obviously extremely hot. Mm-hmm. So I imagine the way that it granulates will probably be different than a cool planet. Like, I can't imagine that the Earth has the same level of granulation. Is that a fair assessment?
Yeah, certainly different stars just to clarify, so stars have granulation on their surfaces, not the planets.
Oh,
but
okay.
Yeah, so the stars have these boiling furnaces, and it's basically the plasma of the sun itself is frothing and bubbling on the surface.
I see.
And it's that bubbling motion which is confusing our telescopes.
I understand. Okay.
Now, different stars certainly will have different properties. In general, stars which are like this, it's kind of interesting. The sun is unusually quiet compared to most stars of its type, which was startling. When we first started looking for planets around sun-like stars, we assumed the sun would be totally typical. And it turns out the sun that we live around is an unusually quiet and quiescent sun. And that made our life harder, right? Because we went out there and we're thinking, okay, all stars will be pretty chill, just like this star. And it turns out most stars are more noisy and active, and that makes our life harder to find planets around them. It's an interesting question, like, why is that so? Is there something about our uniqueness, or, how can we live around such a quiet? If an alien was out there, we'd actually be one of the easiest guys to detect because our sun is so chill. That's kind of interesting. Like, an alien would have an easier time finding the Earth.
If they were using the same measurement that we use.
Using the same technique. Or any of these techniques. Having a chill sun, a quiet sun, makes it easy for basically every strategy of finding planets around it. So we would be unusually easy to find, I think, compared to for a sun-like star. And then when you look at these red dwarf stars, which we mentioned at the beginning of the podcast, these are stars which are the most common type of star in the universe. They're anywhere from 1/10 the mass of the sun up to about half the mass of the sun. They're about half this, about the same kind of size. Yeah, about 1/10 the size to one half the size. Those stars, red dwarf. Yeah. Those stars have giant sunspots on them. So the sun has sunspots, but some of these stars, I mean, none of these. I guess this one here might kind of capture it. They kind of look like this. They're completely plastered in these, and that top right one you can see it as well. Completely plastered in these dark patches that again really complicate the analysis of their behavior. So that has been a big problem. The sun has very tiny sunspots, but these M dwarf stars, these red dwarf stars, seem to be plastered with these giant features, which again makes life hard for us.
Yeah, I guess I wonder if the calmness of the sun is essential to create life. Like, if you have a very, violent and mercurial sun, if that would make it more difficult for life to be created.
Yeah, I mean, you can certainly speculate on ways that could make things harder. For some of these red dwarf stars, they're very violent. The thing to remember about red dwarf stars, they're about the same. I mean, most stars in around us are about the same age. They're roughly sort of, let's say, 5 billion years or so old. That's kind of the typical age of stars in the universe, in our galaxy. Now, the sun will live for 10 billion years. So that means it's about halfway through its life. It's mid-age, like I am. Whereas the M dwarf stars, they live for trillions of years, which I think is crazy. The universe is 13 billion years old. These stars will live far, far longer than the current age of the universe. They will be the last stars burning in the sky, these red dwarf stars. So from their perspective, they're at the very beginning of their lives.
Oh, wow.
And like a teenager, stars are their most violent and crazy and not chill when they're in that adolescent period.
Oh, wow.
And so these M dwarf stars, all of them are teenagers. They're all acting crazy because they're still in their youth. Whereas all the sun-like stars, or by and large, are more middle-age type ages. And so they've kind of calmed down mostly and got off that phase of their life. So that's another problem with looking for planets around those smaller stars. But it's also profound because it means, like, think about the future of the universe. In 1 trillion years from now, those stars will be relaxed, they'll be calmed down, they'll be mature,
dignified,
and they could still have, they'll have, salt and pepper going.
Yeah, exactly.
And those planets around them, which they have many planets, could potentially have life on them, civilizations on them that greatly outlast us. So maybe now they're too violent. And certainly we see that some of the planets we've detected around those stars, which are too close to the star, don't even have an atmosphere. The star is so active, it is ripped off the atmosphere of those nearby planets. Right? That's how much activity and coronal mass ejections and space weather that's spitting out into space. So it's a very hostile place to live around one of those young stars in their adolescence. But maybe as the star calms down, the atmosphere could reform, perhaps delivery from comets or something, or outgassing from geology. It is possible those planets could in the future sustain biospheres, or maybe civilizations like ours might one day move to them, because our sun's going to die. As I said, in a few billion years it'll be done. So where do you go? I mean, these red dwarf stars would be the obvious place to move to, because they will be the last stars burning in the whole universe.
If they're calm enough at that point.
Yeah, yeah.
Interesting.
And
now,
some of them are calmer than others, so you could always kind of migrate bit by bit to them, yeah.
Yeah, we'll try a couple.
Yeah.
Get a realtor,
Try it out.
just kind of see. Location. It's very important. There's something unique about our solar system, so I've been told, and I'm curious how unique it truly is. I guess there's a couple things, but the one that is the most interesting to me is that from the vantage point of Earth, and you mentioned as we're trying to observe these exoplanets, we're looking at eclipses typically.
Yeah.
The eclipse of the moon and the sun is almost a perfect totality.
Yeah.
And this is bizarre because the sun is so many times larger than the moon.
Yeah, it's 400 times larger and 400 times further away.
And somehow they are perfectly, obviously because of the relative distance, they perfectly cover each other.
Right.
Is this unique, cosmically speaking?
It may be. The problem is we don't know. I mean, this is my fault, I guess, but I'm trying to find exomoons, right? That's my main thing. I'm trying to find exomoons, which are moons around exoplanets. That's all they are. And so if we had, a huge catalog of loads of planets with loads of moons, I could give you an answer to that question. I could say, well, look, out of all of these planets, we just don't see this happening at all. Or maybe I'd say to you, actually, this does happen sometimes. But we just don't have any data to really answer that question. It is something people have speculated a lot about. One thing to bear in mind, though, I think is really important with this coincidence, is that it has not always been true. So the moon, even though it is 400 times smaller than the sun, and is 400 times closer to us than the sun is, that's the coincidence, those two 400 numbers being the same number. That ratio is not always true. The size has always been 400 times. You can't change the size, but its distance has been changing. So when the Earth was young, the moon was much, much closer to us. And it's been gradually moving away over time. So this is tides. So if you've ever, obviously everyone's familiar with tides. You get 2 tides a day, a high tide and a low tide. Tidal energy, you've probably heard of that. Like people can tap that energy. You can put, these buoys into tidal bays and things and extract energy from that and use that as a renewable power source. And so you might ask the question, where is that power coming from? There's no such thing as free lunch. Like, where's the power coming from? The power is coming from the moon. It's the gravitational potential energy of the moon that you are tapping. So the moon must be losing gravitational potential energy, and it's actually moving away from us as a result of this process. So it moves away about 1 inch per year, 4 centimeters per year. It is slowly moving away. We know that not only because you can calculate it, but you can actually prove it with an experiment called the laser ranging experiment, which was an experiment the Apollo astronauts put on the moon. So they put mirrors on the surface of the moon, and we bounce a laser off the frickin' mirror every time it comes back. And you can calculate the time it takes light. We were talking about light travel times earlier. How long does it take the laser pulse to go all the way to the moon, all the way back? Do that bounce back. And that tells you a precise laser ranging. You can basically measure precisely how far away the moon is. And we see that even since the 1960s. You can measure the moon is receding away from us. So therefore, we will not have total eclipses forever. I can't remember the exact date, but we will eventually, I think it's like hundreds of millions of years, we'll eventually lose total eclipses. And in the past, the alignment also wouldn't have been perfect. The moon would have been not perfectly sized, but much bigger than the sun, in fact. And so you wouldn't have got that. It would have been totality still, but it would have not been maybe as magnificent as it looks to us, where you have these 2 disks which are almost exactly the same size as each other.
Oh, wow.
So then, why are we living now? That's the more interesting. Why do we happen to live in the entire history of the moon's, period of motion? Why do we live in the one moment in time when you get this cosmic coincidence? I think that's the more interesting. The temporal aspect to me is more interesting.
Right. Well, that is, I guess, the assumption that this is the only time humanity has existed.
Yeah.
Which, I guess is potentially up for debate.
Yeah. Perhaps there was past civilizations on the Earth, actually this is a credible idea. It's called the Silurian hypothesis, that there could have been, as far back as maybe 350 million years ago, there could have been a civilization on the Earth. And they would have looked up at the moon and they would have seen total eclipses, but it wouldn't have been that perfect alignment.
I mean, it would have been way larger. The moon would
Yeah,
have...
a little bit larger. Yeah. Probably like maybe a few percent larger. Yeah. So it wouldn't have been quite as magnificent. And if it's a few percent larger, you wouldn't get the corona. So, and if you saw the total eclipse, did you catch it?
Yeah.
Visually? So you noticed there was like the flames almost, which is the corona around the disk of the moon. You wouldn't get that because if the moon was bigger, it would block that out as well.
Which is kind of the nicest part.
Yeah, exactly. So that's
beautiful.
why, I mean, if you were an alien tourist, it's interesting to think like this would be an event that happens very infrequently across the entire galaxy. And so you would think if there was a large civilization out there, a galactic empire, that they would be visiting us to witness that event, right? It would be like the hot tourist thing to do in the galaxy, to come to the Earth and check out this very rare, infrequent event, which only 1 in a million planets has. And especially with an oxygen-rich atmosphere, and everything here is like pretty nice to breathe, and it's temperate. That doesn't seem to happen as far as we can tell. So
maybe that's why they're coming. Maybe
there's more UFO. It'd be interesting if there's more UFO reportings during total solar eclipses. That'd be kind of interesting to correlate. Yeah.
Oh, that's why they're here, dude. They're like, they have beaches
right.
and eclipses. This is beautiful. This is amazing. Yeah, we think it's for us, but really they might just be looking at the sun.
Right.
We're so human-centric. We're like, they're obviously here for us.
Yeah, we're just in the way.
Yeah, exactly. They're like, oh, you're going to charge us probably for parking. It's going to be a whole nightmare. Oh, this is
humans are the worst.
Yeah, it's just so interesting. I guess the nature of these eclipses, and just even thinking of like from the Silurian perspective.
Yeah,
like the idea that it would be different. Is the Silurian hypothesis? Is this putting a specific time parameter on some prior civilization on Earth? And what is the footing on this? I know this might be technically outside of the purview of astrophysics, but
no, I think it's something I think it's really fun to talk about because it actually does have a lot of impact. And one of the things I'm most interested in is life in the universe. And so I think this is a really important question. If we are the first ever civilization on the Earth, that seems to imply that intelligent life, civilization, whatever you want to call it, is a rare phenomenon, right? Because in the 4 billion year history of the entire planet, you've just got one instantiation. So that would seem to imply it's unusual. But the Silurian hypothesis proposes that there could have been, it doesn't say that there is, it just says there could have been a past civilization. And I'm not talking about sort of the last 10,000, 20,000 years, which sometimes people talk about like a lost Atlantis type civilization. I'm talking about, millions of years, even pre-humanity. So before we even evolved as a species, there could have been another species, perhaps like a lizard or something, some kind of reptile during the dinosaur period that actually did start a civilization. And you might think, well, that's preposterous because surely if there was, a New York City built by another civilization, like we would have known about it. You'd dig it up and see it. But there was a paper written by Adam Frank and Gavin Schmidt that, and their colleagues of mine actually, and they carefully looked at this and said, actually, that's not true. The vast, vast majority of evidence that would be left behind would be destroyed as a result of just the geological reprocessing of the surface of the planet. And so it is possible that there was a past technological industrial civilization on this planet that would be almost erased from the geological record, as long as it's fairly far back, and we're talking like many millions of years back. Probably the earliest you could imagine it happening, in my opinion, would be during the Cambrian explosion. So this was 550 million years ago, basically 500 million years ago. And that's when animals first evolved. So before that, everything's single-celled. So I don't see how you could have a single-celled organism forming a civilization. That just seems preposterous. But once you start having animals, I think that's the earliest point in which you could really push the dial to say maybe a civilization could emerge during that period. And certainly if there was one during that period, it'd be very difficult to rule it out. The only thing we could probably rule out is that they didn't go to the moon. Because if the moon does not erase its surface. So the Earth's surface turns over and is eroded and, all of that information gets deleted. But the footprints of Neil Armstrong, the Apollo landers especially, the Apollo landers will be there for billions of years. Like they're not going anywhere. There's no rain, there's no wind, there's no process to destroy those things except for micrometeorites. And if you look at the timescale of micrometeorites, you're talking at least billions of years.
Plasma erosion wouldn't affect it?
I mean, it would affect it, but it's not going to, I mean, that's a big old chunk of like, I don't know how many kilos, it's probably like a ton or something of mass that you have on the surface of the moon, right? That's a lot of metal to erode away. Nobody has actually calculated exactly how long it will last for. We know the footprints, I think, are estimated to last for about 2 to 3 million years. Just due to the slow accumulation of dust will eventually fill them out. No one knows exactly how long the Apollo landers will last. And I've been actually urging colleagues of mine to think about that and try and work on it with me. But my best estimate is that we have a project in my own team where we've been trying to tackle this by looking at the meteorite cratering data. And yeah, my best estimate is that you're looking at billions of years, which is interesting because then that totally rules out basically any past spacefaring civilization on the Earth, or at least one that went to the moon. No past civilization went to the moon and left something larger than a meter, because that's sort of the scale that we've imaged the surface of the moon to, about a meter. There's nothing there that would be alien.
I see. Now, do we have any prediction as to what the habitability of the Earth would have been like 500 million years ago?
Yeah, it's hard to obviously reconstruct climate all the way back that far, but there are certainly lots of proxies and precursors you can use to try and estimate this. For instance, I don't know if ice cores go quite that far back, but that's one of the classic techniques to do, paleoclimate science, is that you go to like the Antarctica, you dig an ice core, and because each layer of snow kind of builds upon the next layer, you're kind of going back in time when you dig down. And so you can take these long tubes, these ice cores, and then you can catch little bubbles in the ice. And those little bubbles are essentially little samples of what the atmosphere was like. You can even get the temperature by looking at the ratio of hydrogen to deuterium in water. So there's heavy water and there's water, but in about 1 in 100,000 hydrogen atoms are deuterium, which is the heavier isotope of hydrogen. So rather than just being one proton, it's one proton plus a neutron. That's what a deuterium isotope is. And what happens is if you take water and you expose it to sunlight and evaporate it away, the hydrogen will evaporate sooner than the deuterium, because deuterium is heavier. It's twice as heavy. So if you expose something to a lot of heat, you will get a mismatch in the ratio, in the natural intrinsic ratio of hydrogen to deuterium. So you can use, therefore, the ratio of the ice of hydrogen to deuterium to figure out what the global temperature was at the time. So you can do all these kind of very...
But how far back does Antarctic ice go? Certainly not 500 billion
No,
years.
I don't think it goes back 500 million years. So
billion.
yeah, I think they're going back maybe millions of years at most in that case. So there's, I don't know exactly how they go, to be honest, all the way back to that far, to 500 million years. But there are many proxies, and I think you can look at like mineral kind of proxies as well to see how they're depositing.
And then in terms of like tidal behavior, like if the moon is closer, is it possible that the sort of tidal behavior on Earth would be such that we would just be overcome by tsunamis and there's no habitability?
No, not that far back. I mean, certainly if you go back to when the Earth first formed, yes. So when the Earth first formed 4 billion years ago, the moon would have been massive. It would have been in our sky, and it would have been about probably 100 times larger in our sky. It would have been like really a crazy sight to behold, to see this giant moon in your sky. And then the tides it would have raised would be so large that, oceans were just in the process of forming then, but the oceans that were forming would have covered basically the entire landmass of the Earth. That would have been so large. So then, yeah, that's actually thought to be potentially advantageous for life, because one of the possible starting places that life could have begun is a rock pool. Right? So if you've ever been to the coast and you see those rock pools, you see little crabs and things crawling around the rock pools, we think those rock pools are actually quite interesting places where life could have begun, because you put, this salty brine water in a little container, almost, these little pots of rock, and then the sun will basically concentrate the minerals inside that. As it evaporates away, you're going to get more and more interesting chemistry and less water. And so potentially things can combine and start to spawn life that way. So on the early Earth, the fact that the entire landmass would have been covered with these large tides is thought to have been one argument why having a big moon could have been a good thing, because the big moon caused those large tides, it caused lots of rock pools, and therefore it kind of maximized the probability of life starting.
More statistical likelihood that there's a rock pool that the sun can basically concentrate, get some aminos going, and then abiogenesis.
Now, this is obviously speculation, right? There's no...
I think it's a law. We've just done it today.
It's a law.
Kipping's law.
Law of how life began. We wouldn't go as far to say that this is definitely true, but it is an interesting hypothesis that this could have been how life started.
Yeah, I mean, the idea of a prior civilization 500 million years ago is just, and furthermore, to not make it a part of the Anthropocene, I think is actually significant. Yeah, I don't know. I think we get, again, as human beings, a very Homo sapien centric view of existence, obviously, right? Because everything is from the vantage point of like our own consciousness. But even just researching, like, are you familiar with Homo floresiensis?
Yeah. This other species of humanity, the little dwarfs, the hobbits.
And they were seafaring.
Yeah.
According to, some research that I've read. But the idea that we have these fairly advanced, non-human
well, they
beings.
are human, but...
I guess.
But
non-Homo sapien, I guess. Yeah. But, these sort of like, I don't know, I think it kind of breaks my brain to think about like, like they have consciousness and they're thinking and they're sailing around and hunting, and but they're not the way that we sort of perceive humanity to be. You almost have to wonder, like, what is, I think we have a linear view of like human development when that might not be the case at all.
No, the emergence of intelligence is so fascinating. I mean, talking about this deep time aspect, the thing which I'm most jazzed about in the last couple of years in terms of this whole question has been the future. Because the Earth will remain habitable for a long time, probably about 1 billion years. 1 billion years. Now remember, animal life, all animals only began 500 million years ago. You've got twice that still to go on the Earth. That's going from single-celled stuff all the way to us. You can do that twice over still. So think about that. Like, what is the potential for life's diversity? And so we kind of assume, we're the single realization of intelligence on this planet, but there's so many intelligent creatures on this planet already. Octopus, ravens, parrots, different hominid species that we've just seen. And so you might imagine one of their descendants, even if it's not us, one of their descendants will take up the mantle and become a civilization one day. Even if it's 10 million years from now, humanity is only 1 million years old. Even go 10 times that, 10 million years is nothing compared to 1 billion years, right? So there could be many, many rises and falls of technological species on this planet ahead of us. And they would look back at us and have so many questions and curiosity. Like, they were the first technological species. What must it have been like? They were in the Garden of Eden. They had all the oil. They had like all the rare earth materials, and they caused a fucking mess on the planet. Right? They really messed things up. But the Earth will heal itself, and so whatever damage would, even if we go full blown on climate change, you go 10 million years into the future, and most of that's reset. So we're probably going to screw ourselves over. That's, I think, the main reason I'm concerned about climate change. But the Earth itself and future species will be fine. I think that's going to all recover, and that makes me really excited about the possibility that we should leave something on the moon for them to find. Right? I want to leave them a message. I want to leave them a time capsule and say, like, we anticipated that you would pop up. We thought about it. We realized there was a lot of time left on the clock. We realized we were probably not going to be here forever. And we have left you this time capsule of here's all of our art, our science, here's who we were. And I think that would be a really profound project to do.
Yeah, how do you communicate a time capsule to future... would this still be considered human, I guess? Like, if it's...
not necessarily human at all. Yeah. I mean, there could be a descendant of a dolphin, right? I mean,
right. Yeah, how do you communicate to a future intelligent being what we are?
I mean, that's the whole thing with talking to aliens that people forget is how hard communication can be. Like, why would they understand anything we're saying?
So many assumptions.
Like, Star Trek never really deals with that too well. But we can't even communicate with humpback whales and dolphins, which are basically the most intelligent other species on this planet. We do not have a way to really converse with them in terms of abstract thought. We can maybe give them like direction, like go pick up the ball or whatever. But you can't truly understand the mind of a dolphin. And so and that's an extremely closely related relative to us. So why would we expect that a completely different alien species that's maybe not even based on DNA or carbon, why would we expect that we would have any mental commonalities to even have a dialogue like we're having right now?
So now this raises the question, if there was a prior advanced intelligent species, human or otherwise, perhaps they had the same thought as us and said, we will leave them a time capsule.
Yeah, and which is like the 2001 Space Odyssey type
right.
thing. Yeah.
But we don't have the ability to decode it because of the same problem that we're having in the future.
Yeah, maybe we're not even recognized. I think if we'd found it, that would be a big story of itself. It says, just discovering like if you discovered a cube buried, a meter under the lunar regolith that was like the monolith that they had in 2001.
Mm-hmm.
That's one thing. That would be pretty profound already. Like, okay, someone manufactured this thing. I think we could probably tell just off the bat. Figuring out what it actually means would be something that would probably take us generations, right? Because there's even languages of humanity that we can't decode. And there's a language called Linear A. It's like in the ancient Greek kind of period that we cannot decode, but we can tell. There's actually a cool mathematical trick they've been able to apply to tell that it really is a language and not just random scribbles. There's something called Zipf's law. Have you ever heard of Zipf's law?
Mm-mm.
Zipf's law is a rule that says that the most commonly used word in the English language is used twice as much as the second, 3 times as much as the third, 4 times as much as the fourth, and it holds all the way down to, I think, the 40,000th most commonly spoken word, and it happens in every language ever spoken, not just English. Every single language this happens for. It even happens for humpback whale calls and dolphin clicks, but it doesn't happen for squirrel monkeys or baby gurgles. So it seems like it really delineates between useful communication, intelligent communication, and just random noise. And so in this ancient language, Linear A, they can tell that it matches the frequency of Zipf's law. And so even though they can't figure out what it's saying, they're pretty confident that it really is a genuine language because it matches the same pattern.
Because there is a word that is used X amount.
Yeah.
And then there's another word that is used.
Or a symbol, yeah.
Or a symbol that's used half that amount.
Yeah.
And then another one, or I guess not half, but I guess. that descending
So we could
order.
probably tell that if we had an alien message, we could probably figure out whether it was actually a real communication. I think, using these kind of patterns, assuming this holds beyond just the Earth. I mean, I said it works on every language on Earth and even other animal species, which are quote unquote intelligent. By extension, you'd think it would apply.
It's an intelligence function rather than, the structure of Germanic languages or otherwise.
Yes. Well, yeah, it's interesting. I mean, there's a lot of theorizing about why this happens. It may be, there's some kind of redundancy. To say one word many, many times seems redundant. But it's syntax. It's the syntax words that we're using. It's like the, and, it's those kind of words that pop up so often. But those words are there because they allow for sort of a greater ease in reconstructing the message. So even if you didn't hear every word I said, you didn't hear I said, you could still probably guess what that missing thing was, word, right? So you can still probably figure that out because the syntax gives you the context to interpolate the missing word. So I think that seems to be a common feature of useful languages, that you have to have some kind of redundancy so that you can fill things out through audible communication.
Wow. Yeah, but then you wonder, is that restricted to Earth because we all have the same common ancestral development?
It may be. I mean, this is the best we can do. All you can do is I mean, this is about as good as it gets. You've got something that works in every language ever spoken, and it even works in other intelligent animal species. That's about as good as we're going to get until we start detecting aliens.
But the vastness of the cosmos, you realize this is such a sort of a fluke event.
Yeah. Well, maybe we'll miss some. Maybe we'll miss some aliens who don't follow that rule, but that's okay. We'll probably catch a lot of them who do. I mean, that's all you can really do.
Yeah.
You're never going to be complete. I mean, people always say, like, how do you know there's not life in Jupiter's atmosphere? Why aren't we sending probes to look for life in Jupiter's atmosphere? Or why aren't we spending lots of time looking for life around a black hole? And it's not that you couldn't have life in those places. We could imagine contrived ways of that happening, but it's just not the most obvious place to look. So you've only got so many resources. NASA only has so much budget. We only have so much time. You have to prioritize. So when we say like we think water-bearing worlds are the most likely to have life, we're not saying that's the be-all and end-all. But it seems logical to start there with your search. At least find if you can get life there, and then maybe flesh out to the more crazy places. So I think that's kind of, people sometimes think that we have this kind of very exclusionary view of where life is, but it's more just pragmatic. It's just like, how do you, with finite resources, maximize your chances of success?
Wow. Okay. We have many other things we need to discuss. Wormholes, time travel, black holes, the end of the universe, heat death, all of these things. But we're going to take a quick break just to hear from a sponsor that makes this show possible. Thank you for everyone that's watching live right now. If you have any questions for my dear friend Dr. Kipping, please write them in the comments during the break, and we will come back with a couple. I say your choice. We'll just go through a couple of them, and then you pick your favorite.
Cool.
And we'll just come back on that. So please write down a comment, and we'll be back in just a second. What's up, guys? We're going to take a break really quick, because if you're anything like me, you're probably running late. All the time. I am. I'm always leaving right when I'm supposed to be somewhere, and I never have time to sit down and grab a nutritious meal. And that's why I want to talk to you about this little product right here called Huel. Huel is absolutely amazing. It's got everything you need, all the essential vitamins and minerals, all the nutrients, all the protein you need in a regular meal, packaged in this beautiful, convenient little bottle. That's right. No more of the days of you running out the door being like, oh, I'll just grab some fast food or something. Oh, I'll have like the leftover cheeseburger in the fridge. No. With Huel, it's healthy, nutritious, everything you need to power through the day, served in this little bottle right here. I mean, this has got 35 grams of protein, 7 grams of fiber, 27 vitamins and minerals. Everything's right on the back, and this will help you get through the day. It'll help you perform better, not only in the workplace, but also in the gym. I mean, at this point, I think they've sold over 400 million meals. I mean, is it 400 million? I mean, that's amazing. 400 million meals. So why not you? Take control of your health, be a little bit more time efficient, and get all the essentials that you need in every little bottle. If you're interested, go to Huel.com, use the promo code CAMP. That's Huel, Huel.com. Use the promo code CAMP and get 15% off your first order. Check it out right now. Get control of your health, get control of your life, and stop being so late. Let's just fix that also. Be on time, all right? Set an alarm. Let's get back to the show. What's up, guys? We're going to take a break really quick because I want to help you make sports more fun. That's right. If you like watching sports, there's a way to make it 10 times more fun, and that is with Prize Picks. Prize Picks is the largest independently owned daily fantasy sports platform in North America. It's absolutely super fun and super easy to play. All you got to do is pick 2 to 6 player stats and hit more or less, and you can watch the winnings roll in. And to be honest with you, I'm pretty good. I've been winning some money, but I've lost more. I'll be honest. I'm bleeding money right now. I'm terrible at this game. I know nothing about sports. I'm awful. I always click more or less on the wrong things. So whatever I do the exact opposite of. Apparently, people are winning money on this. There's some people that are making, they turn $10 into $1,000 with just a few taps. Not me. Maybe you could figure it out. So if you want to play Prize Picks, go to the App Store, download the Prize Picks app on your mobile device. Use the promo code CAMP, C-A-M-P. And with your first $5 lineup, you will get $50 instantly deposited into your account that you are able to play with. That's right. I mean, here I am, giving the good people some funds to play with. So, you're welcome. Now let's get back to the show. Amazing. What's up, everybody, and welcome back. Sorry for the short break. Thank you to Prize Picks for making this show possible. As you know, I'm terrible at this. I just bleed money just constantly. I'm not good. But maybe you'll be a little better than I. And if you're interested, let's just check out some picks, okay? We got Marquinhos, 97.5 passes attempted for PSG. As a defender, I'm saying more. Marcus Alonso, I'm going to hit less on that one. And then Dame Lillard. Yeah, when are they playing? Is that tonight? That's tonight. Dame Lillard, 23.5 points. I'm going more. Come on now, you got to go for Dame. I trust him. And if you're interested in playing, you can download the Prize Picks app, or I think it's in the description of this video right now, so you can get it there. Thank you so much for Prize Picks for making the show possible. We're here with David Kipping, the legend, the Man United supporter. So I hope that polarizes the audience.
When I was a kid, yeah.
Immediately, damage control.
I want to try and back out of it a little bit, yeah.
No, this guy's a big time, still a passionate mani sport. He won't stop talking about it. So we got some questions from the audience. This one I thought was interesting because it has a word I've never heard before. This is from Benjito. You believe humans will migrate to artificial habitats like O'Neill cylinders in the coming generations?
Yeah, so we should explain.
Oh, that's from Benji. Do you believe? Okay, syntax. That's
but we should maybe explain O'Neill cylinder because that's a bit of a fun concept. So,
yeah, what is that?
I guess it's trying to solve the problem of gravity in space. So, one of the big problems with the astronauts on the ISS is bone degradation, kidney stones, decalcification of the bone, and it causes all sorts of health problems. And so you can stay in orbit for maybe a year, 18 months. I think it's kind of the record that astronauts have been up there for. But once you go beyond that, it seems unsustainable. So how do you produce some kind of microgravity or even semi-gravity environment in space? Rotation. And this is what these cylinders are trying to do. So you imagine like a giant cylinder in space, and these things are, can be hundreds of meters across or even kilometers across. So it's going to be challenging to build something that big, but maybe one day we can pull it off. And you rotate it around the central axis. And as it rotates, think about being on like a merry-go-round or something. As it spins around, you get pushed to the outside. Mm-hmm. And so everyone will be pushed against the inner wall of the cylinder. And so on that inner wall, you build your buildings, you have your parks, your lakes, and people just walk around the surface. It is a little bit disorienting because as you look up, you would see another building like upside down.
I think Interstellar draws.
Yeah,
this,
Interstellar
correct?
has this concept. But it's thought to be one way that you could produce a kind of quasi-Earth-like environment in space.
Interesting. Basically using, what is that, inertia?
It's essentially inertia. Yeah, so you're rotating it and objects want to travel in a straight line, and so they're being pushed against the walls because their own inertia wants them to keep going straight, but instead there's an object there, and so you feel that resistance against that object.
Like, don't folks on the space station, I guess astronauts is what people call them, astronauts on the space station, folks, don't they use like gyroscopes to exercise? I don't know if
gyroscopes. I don't think they use gyroscopes. I think I've seen them run on treadmills and they kind of tape themselves down, right? They put all these straps on them to kind of produce like an elastic version of that kind of gravity. But
I had seen these like little mechanisms where like it's basically like a sphere within a sphere, and there's basically like a ripcord on it that you can pull, and it moves the internal sphere. So as you move it around, it creates a resistance gyroscopically.
Yeah.
And so as a result, they're able to like kind of use it as almost a way to create like resistance training.
Interesting. Yeah,
while in zero gravity.
Yeah, one issue I'd imagine with that, and essentially whenever you have a rotating structure like with these O'Neill cylinders, you could be like, well, why not just make it really small? Make it like 10 meters across or something. The problem is the smaller you make it, the ratio, there's two forces that actually are in play. One is basically the centrifugal force, which is your fake gravity. So that's the artificial gravity grid that's pushing down. But there's also going to be another force called the Coriolis force that actually acts in a sideways direction. So if you imagine this whole thing was rotating, if I drop the ball, it's not going to fall straight to the ground. It'll curve off to the side because the whole thing's rotating. So that sideways force becomes stronger and stronger the smaller, compared to the downward force. The ratio becomes stronger and stronger as you get smaller and smaller. And it becomes really disorienting. So if you're walking around in that, you're going to be like constantly like lurching to one side, and if you change direction, it will kind of feel weird because it will go the other way, and so it causes really bad headaches and disorientation. So there's been studies where they've actually put people in simulated environments like that on the Earth in rotating structures, and even test pilots they put in who are great at dealing with high G forces. And then they ask them to do like basic tasks, like just add up these numbers and write some computer code or something. And once the sizes get below about 10 meters or so, they can't do it. They're just too disoriented because of this extra force. So if we're ever going to build these, they probably do have to be, unfortunately, quite large. So you probably need some kind of space manufacturing. So I guess to answer the question, I could see it happening. It's not obvious to me that that's any easier necessarily than just colonizing Mars or building a base on the surface of Mars or the moon. That seems more straightforward to me rather than building this giant kilometer rotating structure. These things also are at risk of tumbling, right? So there's an effect called the T-handle effect that astronauts have. There's a really cool video, maybe you can find it, of an astronaut spinning like a T-handle. It's also called the tennis racket effect, I think. And if you spin it, it will spin as you expect, but then suddenly it like rapidly rotates. It just completely flips direction. And that's because it is rotating around not its primary moment of inertia, but one of its intermediate moments of inertia.
Because it's not perfectly the right...
Yeah, I think here's the video right here. That top one.
Yes, I've seen it with a hammer. It's like a hammer type thing.
So look at this. You see that?
Right, because it's...
So that could happen to your whole cylinder in space,
I see.
which would not be very pleasant to just suddenly flip over like that.
And is this because there's like multiple axes that are effectively like pulling the...
Yeah, it happens whenever an object rotates about its intermediate moment of inertia rather than its principal moment of inertia. Actually, you can rotate around either the principal or the lowest, but if you rotate around the middle one, which is what a cylinder always will be because it'll be along the middle, it causes this kind of flipping effect. So then the way around it, I think O'Neill, who came up with this, imagined, I think, 2 cylinders that would somehow be tethered to each other and kind of prevent this effect from happening. So it has some risks, some issues with it. I think it would just be easier probably to build a base on the moon.
And when you say a base, do you mean with some type of artificial gravity?
Well, I mean,
using the moon's gravity.
Yeah, the moon's gravity is probably enough, I think. I mean, it's unclear, but it's probably enough, I would guess, to avoid most of these detrimental health issues. It's 1/6 the gravity of the Earth on the moon.
Have we tested that? What 1/6 the gravity?
Well, it's hard. I mean, how do you test that?
Yeah, I mean, can you model it?
You can't. Basically, you can't get rid of the Earth's gravity. That's the problem. So.
But is there any modeling where you can use like computers to test like what that would do to like blood flow and like how our brains process things?
Yeah, I mean, possibly. I think I'd be skeptical about any of those results though, because modeling a human body is pretty damn complicated. Yeah. So I'm not sure I'd really trust any of those results.
Yeah, fair.
You really just need to put, maybe they could do it with a mice or something. You could put a mouse in one of these centrifuges in the ISS at 1/6 gravity. Maybe they've done that or something. I don't know. But I think, Mars certainly, I think that's like half the gravity of the Earth. So you'd think that would really be fine. Maybe the moon's a bit more on the borderline as to whether it's okay or not. But I think certainly being on the ISS or even on a space vehicle that's going from Earth to the Mars, I think that's the main concern. We want to one day go to the Mars. That journey is 18 months. 18 months, you're not only going to have a lot of bone degradation, which is a major health concern, you're also exposed to solar radiation for a long time as well. So you have to have a lot of shielding to protect the astronauts. On the moon, that's actually pretty easy because there's so much lunar soil. You just put sandbags on the top of your base, and those sandbags are great at protecting you from solar radiation. So whenever you're on a planet, I think it's somewhat easier, practically speaking, to imagine how you would do that.
And the bone degradation occurs because there's no resistance, and that our bones need resistance.
Well, less gravity. Yeah.
Right.
Yeah. There's essentially resistance. Yeah.
You just need milk, I think.
So you can maybe do like a ton of like protein enhancements.
Yeah, exactly. If you got a dairy allergy, you can't go to Mars.
Right, but they might actually figure out a way of like genetically engineering people to deal with these conditions one day. I mean, that's an interesting possibility.
Yeah. Another question.
It's not going to be us though.
You can punt on this if it's not interesting. We can avoid it. But Boots Void. Is that how you pronounce that?
Yeah, I'm not so familiar with Boots Void. I think it's just I'm not sure if it's some of the voids are not genuine. Can we put up a picture of it? Because some of the voids are actually
this is a real thing. I hope we're not getting pranked.
No, it is a real thing.
Okay.
It's definitely a real thing. I think this is just dust, if I remember correctly. Yeah, I think is it this one?
Oh,
I think this is,
Croesus, can you go to the one 2 to the left?
Yeah, so I think the point with this void, and again, I am punting a little bit here without looking it up in detail, but my understanding is that is not a real void. There is just a whole bunch of dust in the way.
Can you explain what we're looking at?
It's just a star. It's just an image of a distant star field.
And there's just a giant...
So, there's stars everywhere, as you expect, but there's this one area that appears very dark. But this is, I think, only true in ultraviolet and optical radiation wavelengths. So if you move towards the infrared, which I suspect is what this image is on the left, as you move towards the infrared, you can see stars. It's only in the optical you don't see it. So it's the same effect we were talking about earlier, how blue light gets scattered more easily by dust and red light makes its way through. So if you look in red wavelengths, infrared wavelengths, the light just passes straight through the dust. But if you look in blue wavelengths, you don't get the light passing through. So it's not a real void. It's just a big clump of dust, I think. in this case that's in the way. But there are some real voids, but I think they're more on the galactic scale rather than a stellar scale. So there's areas of the universe where there seems to be a real dearth of galaxies just due to the kind of cosmic architecture of the universe itself.
And what is there any practical explanation or theories as to why these voids exist?
I think to some degree you expect voids. Like there's always going to be regions of overdensity and underdensity. And remember, gravity tends to want to bring objects together. Mm-hmm. So if I start out with some homogeneous mix of galaxies and I just slightly perturb it, then there'll be an area where the galaxies will clump together, and then necessarily there'll be an area where they did not. So just the nature of gravity wanting to clump stuff will lead to voids.
What is the Oort cloud?
The Oort cloud is in our solar system, or even the edge of the solar system. So there's the asteroid belt, which is in between Mars and Jupiter, which is probably a failed planet that was trying to form, and Jupiter got in the way and stopped it from forming and disintegrated it.
R.I.P.
Yeah. Then you go further out, you got the Kuiper belt, which is kind of like another asteroid belt. It's similar, the asteroid belt is kind of coplanar. It's like a disk. It's like a ring of material in the solar system. And similarly, the Kuiper belt is kind of like a ring of material. And the Oort cloud is different because it's not a ring. It is a big spherical shell around the entire solar system. It's still somewhat unclear whether it really exists or not. We don't know for sure that it exists, but it is strongly hypothesized to exist as the source of comets. So we see comets come into the solar system from the very edges, and they kind of swing past the sun and come out. And so the question for a long time is like, where the hell is all this stuff coming from, these icy objects? So it's thought that there is this cloud, this great collection of icy, rocky material out there in the outer solar system. This stuff is really far out, like of order of like a light year away from the sun. So this is like really tenuous material. Sometimes in sci-fi they fly through an asteroid belt and it's like super dense and the ship's like dodging left and right.
Yeah.
This would be totally different. The rocks would be like, many, many hundreds of billions of miles away from each other. So you wouldn't be able to see, if you're at one rock, you wouldn't see anything else in there. It'd be a very sparse region of space. But nevertheless, sometimes the gravity of Neptune, the gravity of Uranus could perturb them and kick them in, and that's what causes the comets. So I think what's really fun about the Oort cloud, I've been thinking about recently, is because it's of order of 1 light year-ish around us, even a bit more than that, and stars are typically separated by a few light years, like the nearest star is 4 light years away, that too will have an Oort cloud around it, presumably, of, again, about a light year scale. And sometimes stars will pass pretty close to each other, and so there could be a mixing of this material. So our Oort cloud might not necessarily all belong to the sun. Some of it might have been material that actually formed around a completely different star and then got mixed up with our Oort cloud. And so some of the comets that are coming in are perhaps, in fact, material that once belonged to a completely different star system. And so there's a huge interest right now in trying to sample these objects. There was a very famous object called Ommuh. Did you hear about this? There was an interstellar asteroid. So it was detected, I think, 2017. It was the first one ever found. I think so, and I think we now know of 2. And it was an object that was moving so fast through the solar system that there was no way it could have come from the solar system. It had to have come from outside the solar system. And so it passed through and it's now leaving the solar system. Next time we're hoping to catch it. We could get a spacecraft, we could catch up to it, we could maybe land on it, scoop up some of the material and sample it. And then we would have for the first time a sample of material that was interstellar, that was from a completely different star system altogether. And we could probe is the chemical building blocks that we find in basically, the basic materials like amino acids, carbon materials, are those same ingredients present in other solar systems or not? And that's kind of like a shortcut, right? Because otherwise the only way to do that would be to fly all the way to another star system, land on the surface and scoop up. And the universe is kind of offering us a shortcut. It's going here's a sample. Just grab onto it, get your fishing net out, catch it, and you can answer this question kind of for free. So I think these things are super cool.
Is it realistic to land a craft on these super fast-moving?
It's hard. There's a proposal. I don't think it's funded yet, but there's a proposal to do it. And the idea is that you'd have to have the spacecraft launched basically now or in advance. You launch it and you put it in an orbit around the sun, and it's just kind of waiting there. It's just kind of like got its engines fully ready to burn, and it's just like on the lookout. And as soon as the astronomers detect the next interstellar asteroid, it goes full burn, just like heads straight to that thing, and you can catch up with it unless the velocity is really extreme.
Do we have any predictive ability to know when the next interstellar asteroid is coming?
Not really, no. It's just a waiting game for that. There's a new telescope that should come online in March next year, in March 2025, called the Vera Rubin telescope. Used to be called LSST and got renamed to Vera Rubin after one of the astronomers attributed to the discovery of dark matter, Vera Rubin. And it's a giant 8-meter sized telescope, and it's thought that will be really good at finding these things. So it's thought that should find about of order of 10 per year. So far, we've only found one, but if you just take, or two, if you take the rate of those things, so we found 2 over, say, 10 years, and then you say, well, what happens if we had a telescope that was like 100 times better? Then you would end up getting about 10 per year. So it's thought that Vera Rubin should find a whole bunch of these things, and then hopefully, we could get an interceptor to catch up with it and have our first ever sample. And Ommuh is super interesting. I mean, Avi Loeb, I don't know if you've heard of Avi Loeb before.
Absolutely.
But he has speculated that could actually not even be a natural asteroid at all. It could be a spaceship, right? Because some of the properties of that thing, I don't buy into the theory. I think it's a little bit speculative, but it's interesting to ask the question, and a sample return mission would conclusively resolve that some of the properties of that asteroid did look a little bit suspicious and fishy for a natural object. It had a very strange shape, for instance. It was 10 times longer than it was wide. And it's kind of like a cigar, basically. And so there's no object. It's very rare that you get objects in the solar system that look like that. But that ratio might be the kind of ratio you would build if you were trying to build like a solar sail or a spacecraft or something. So, yeah, and it had some very unusual colors. Like when we take the spectrum of it, it didn't look quite like a normal asteroid.
How large is this?
I think it was of order of sort of 30 to 100 meters kind of scale.
Wow.
Yeah. So it's like Rendezvous with Rama, which is an Arthur C. Clarke story. There was this idea of a cylinder spaceship that entered the solar system and just kind of parked its way outside the Earth, and people were freaking out, like what to do about this spaceship. And this thing did not park. It definitely came all the way around the sun. It was also tumbling the whole time. We showed that T-handle tumbling. That's what this thing was doing. It was tumbling exactly the same way as that T-handle all the way around. And so for me, that's like this. How can that be a spaceship? Like, why would anyone fly the spaceship tumbling around like that? It's pretty strange to me. That would be a natural. That would be a way that you'd want to fly your ship.
But what a great movie, though.
Yeah.
Where we go and we're like, okay, let's go, culture the space rock. Yeah. And then it turns out to be a spaceship. And then they see it as an act of aggression.
Oh, yeah.
And then we start a galactic space war.
Right. And the most intriguing thing about that rock is it actually accelerated a little bit. It didn't really accelerate, but it didn't decelerate as much as it should, I should say. So as it's leaving the solar system, the sun's gravity is like pulling back on it. So it's kind of like when you like a slingshot, you go past the sun, you accelerate as you get close to the sun. And then as you go on the back way out, you're decelerating. But instead of decelerating in the way we expected it to, it seemed to have more speed than it should. And so it was suggested by Avi that, this is an indication that there's some kind of engine or propulsion system that's doing this.
Oh, how fun.
So that's kind of wild. There's an alternative explanation, which I think is more credible, that it was just outgassing. Lots of comets do outgas as they leave the solar system. So it's possible there was just material coming off it. One of the controversies there is that we didn't see any material coming off it, and we looked. We didn't see anything coming off it. So how could that be happening if we didn't see it? And I think the answer to that is we didn't look completely thoroughly. There's certain wavelengths of light which we didn't span. We were expecting a certain type of gas to come off that thing, which is typical in the solar system. But instead it could have been producing, I think the proposal was carbon monoxide or carbon dioxide, like a solid carbon monoxide or dioxide gas. Ice could have then sublimated, and our observations were not sensitive to that particular molecule. So there's some wiggle room there that you can imagine, well, just because it accelerated doesn't mean it has to be a propulsion system. There could just be some boring ice that we didn't check for that came off the surface.
Oh, so interesting.
But it's still really interesting. And I think, look, whatever you think about it, we should find more of these things. Let's do it, and we should investigate what's really going on.
Wow. Yeah. Again, going back to the light thing, I don't want to harp on this, but like we're so, I don't want to say limited, and I say we as if I'm doing any of this, but humankind. Okay.
You're in it. You're
I'm a human.
Team CoolWorlds.
I'm a human. Like we're limited by, what we're able to detect in terms of, measurable light on the spectra.
Yeah.
So I'm curious, like when we look at the spectrum of light from like infrared to, gamma and anything on that spectrum, are we confident that is all the light that is possible, or is that just what we're able to detect?
Yeah, I mean, light can be almost of any wavelength, right? So there's always a wavelength that you're not searching for.
So it is possible that there are certain wavelengths that we're not able to detect
that
sure. exist outside of the spectrum that we just haven't discovered.
And not just, there's many axes that we're not checking. So even if you have a telescope, I mean, no telescope can detect all wavelengths of light at once. Each telescope can detect a certain range. And it looks at a certain patch of the sky, not all patches of the sky. And it only looks at that patch of the sky for a certain time. So there's time, space, and wavelength. Right? And we are only covering a fraction of each one of those three. So we definitely don't have a complete view of the sky.
Yeah, it's like scooping a net in the ocean every hour and being like, oh, we didn't find a fish.
Right.
And it's like, well, the porousness of the net and the time you're doing it and the part of the ocean you're doing it in, I think that just puts into sort of scope. Again, maybe this metaphor isn't exact, but it puts into scope how much might be missed or undetected.
It's a great analogy. In fact, there was a paper by one of my colleagues, Jason Wright, who used that exact analogy and calculated, he quantified it. And he was talking about the search for aliens. He said how much, he was thinking about radio astronomy. One of the ways we look for aliens potentially is to listen to their communications in radio waves. Maybe they don't communicate in that way, and so we won't see anything, but he did the calculation, like how much have we covered? Because again, with radio waves, there's all different frequencies of radio waves. And there's different modulations, AM, FM, that you could use for the communication, polarization, all these different ways you can do it. And I think he found in total it was like 8 or 9 ways that you could, like axes that you can think about designing a signal. And our coverage is akin to exactly your analogy of like dipping into the ocean of a hot tub. It was like filling a hot tub with water of the entire ocean and claiming, okay, there's no fish in there, therefore there's no life in the universe. That would be the conclusion you would arrive at. And obviously that's false, right? Because if you take a random bathtub of water, chances are you would not have a fish unless you're in a fortuitous area or something. So it goes to show you just how little we have scanned. And I think this field is called SETI, the Search for Extraterrestrial Intelligence, SETI. And it has come under criticism because folks have said, taxpayer money has been funding this in the past. And taxpayers have rightly said, look, you've been searching for 60 years, and you found nothing. So why should we keep funding this effort?
Yeah.
But here's the thing. We've searched like that much of the parameter space. And the thing is, as technology gets better and better, each year we do basically twice as much as we did the year before. It's kind of the same with the Human Genome Project. When they tried to sequence the human genome, I think they had like a 10-year timescale they wanted to complete it in. And the first year of that project, they sequenced like such a tiny fraction of the human genome that everyone was like, this is crazy. You're never going to complete this in 10 years. But then the next year they did like 10 times as much. And the year after that, another 10 times as much. And they knew that would happen because they knew their technology was improving exponentially.
Moore's law.
Yeah, it's Moore's law. And so they were able to map the human genome in the time they originally said they would. And the same way with our telescopes and our sensitivity, that yes, we've surveyed a tiny fraction, but you've got to think about that exponential law. If we stop investing in this, then that's it. That's the end of the game. But if we keep at it, we'll rapidly climb up that curve, and we will be able to map, eventually the entire galaxy for communication signals at some point, which would be, even if that's a null result, that would be a pretty amazing null result. There are no radio communications anywhere in the galaxy. That would be a pretty profound thing to say. It would put a very hard limit on the types of civilizations which are out there.
Yeah, and the big thing with SETI that I think about is the eye, right? Like intelligence is sort of a subjective thing. Yeah. And you had done a video on CoolWorlds YouTube channel that was very interesting about, I believe it was microfossils. Is that the term? Effectively looking for fossils of
the earliest life.
Yeah, single cell organisms. And there was research done fairly recently, I forget by whom and when, that effectively found microfossils dating back
even further,
a billion years.
Maybe I'll flesh this in a bit. So I think the earliest evidence for life that comes from a fossil, I think a fossil is pretty much incontrovertible. If you have a fossil of something, there was something living there, is about 3.5 billion years ago
on Earth.
The Earth itself is about 4.5 billion years old. So in the timescale, that means when the Earth was 1 billion years old, after its start, you have life, for sure. But the question is like, okay, a fossil is a pretty sophisticated thing, because for something to leave a fossil, it has to be kind of large, like it has to be a fairly large mass of biomaterial to do that. So you might imagine, therefore, there was something before that fossil. That can't be the very first thing that lived. And so people have been trying to like find other ways of pushing this date back. The earliest evidence I'm aware of at the moment comes from something called LUCA, which is the last universal common ancestor, LUCA. And LUCA is based off genetic evidence.
Also, I just want to apologize if anyone's watching live. There's music that just got played outside the studio that I think is going to come down. I don't mean to interrupt you.
Yeah, no, I was wondering if you're going to come.
Yeah. So
they basically take all the living creatures that we know about on the Earth. They take their genomes, and you see common genetic structures in every single living thing. And so that tells us that at one point we all came from the same thing, which was LUCA, this one organism from which all of the life eventually evolved from.
Last universal common ancestor.
Yeah. And they combined basically genetic dating techniques with sort of proxies in the geological record to figure out, and this is, again, not my field of expertise, but they figured out the date was 4.2 billion years old, was LUCA. So LUCA lived 4.2 billion years ago. So that means the Earth became habitable. As I said, I mean, it was born 4.5 billion years ago. There was probably oceans there at about 4.4 billion years ago. So within 200 million years, you had LUCA appear. And LUCA, again, wouldn't have been the very first living thing. LUCA was already quite sophisticated when you look at its genome, because they can figure out what its genome was likely comprised of. And so it appears that life got going really freaking fast on the Earth. And I did a video about that, just saying that, before I was fairly agnostic about whether life is common in the universe or not. Because when you take that 3.5 billion year number, that's a billion years. There's a lot of play. And I did the math on that. I wrote a paper about that, and I showed that it's not really conclusive. You can't really conclude that life is therefore everywhere based off that number. But when you go back to this new date from LUCA, that's pretty hard. That's so early that it basically demands that life is an easy process. And so my needle has shifted. And now I think that simple life in Earth-like conditions, the question is, how often do you get Earth-like conditions? But in Earth-like conditions, I think that indeed simple life starts quickly and easily. That still leaves open two questions. How often do you get Earth-like conditions? And then how often do you get us? How often do you get something that can do technology? That may be incredibly rare still. So I'm still agnostic about intelligent life. It might be common, it might not be. I don't know. Let's do the experiment and find out. But I'm leaning towards optimism about simple life.
Which I think draws into a greater picture of why the research for CoolWorld exoplanets is so important. Because if you can find Earth-like planets, then we have a higher probability of some sort of, single cell, simple, non-intelligent, microbial life existing somewhere else in the universe.
Yeah.
Which I'm curious if there's like microfossiling research being done now on other planets to find those types of, single cell bacteria, things like that.
Yeah. I mean, obviously you need a sample. So for an exoplanet, it's not really possible. You can't really easily fly there, at least with current technology, and get a sample. For Mars, you can get samples. And there's even meteors that we collect which come off Mars. There was a very famous meteor called the Allen Hills meteor. Maybe you could throw it up on the screen, the Allen Hills meteor. And there was, I think it was like 1993 this happened, and Bill Clinton was the president at the time. Allen Hills meteor, you might need to put it in to get it. Bill Clinton stood on the White House lawn. Here you go. If you go to your images, you'll probably see, yes, that thing right there. That thing, that third image.
Yeah.
People looked at that and they said, that's a worm or like some kind of fossilized organism on the surface. And this thing came off Mars. We know it came off Mars. And you see these little biological looking things. And so Bill Clinton came in the White House lawn and he gave a press briefing where he talked about, you know, what seemed to be the first evidence for life in the universe. Isn't that amazing that happened? I think that's crazy that a president stood out and said, essentially, we discovered life. He was a little bit cautious, saying, you know, we still need to investigate, we still need to check it up. But, you know, the world got very excited about this for a while. And of course, as with many things, it turned out to be challenged later. And it was shown in subsequent studies that you could get things like this just from water passing over rock in certain configurations. So these could simply be natural minerals that are forming in certain conditions. You don't necessarily need a living creature to produce that. As eerie as it looks, it is maybe just a purely a product of water and rock mixing together that can cause this under certain conditions.
Wow.
So that could have been a microfossil, and indeed we can still do that experiment, right? So people are still looking for more convincing fossils than that in these meteors, and you can imagine astronauts on Mars. If we ever got a colony going on there, we'd be able to dig up a huge ton of rock and be able to do this experiment and really, you know, get geologists out there, paleontologists out there, and look for this stuff en masse. That would be amazing because I think Mars has a lot of strong evidence that it once had liquid water on its surface. It's unclear if it was prolonged. It might have been an ocean, or it might have just been like flash floods that appeared. We don't know which. But the fact it had water and it seemed to be fairly temperate, it's the right kind of conditions for life, means, you know, maybe life did start there. Maybe even life started there first and then hitched a ride on a meteor to Earth. And we could all be Martians.
Landed in a rock pool.
Yeah, and got things going here. So that's called panspermia, the idea that life could start on another planet and then transfer over to the next one. And so it is quite possible that we are all Martians deep down. And so if we detect life on Mars or a fossil on Mars, I think the first question we might ask is, does it have DNA? Is it connected to LUCA? Is it the same as us? Are we related to it? If we're related to it, then that means that panspermia is definitely occurring between planets, either one way or the other. If it's completely different to us, that would be perhaps even more exciting, because then it would prove that life started on two separate bodies independently. And again, that would sort of verify my hunch that life gets going everywhere. This is it. Life's just par for the course.
Now, an asteroid from Mars, how does that escape Mars's gravity?
Yeah.
Like I'm on Earth, right?
Yeah.
You know, I'm not trying to brag, but I'm here. And the idea of trying to get a piece of Earth off of Earth seems sort of insurmountable. So how does something from Mars actually end up on Earth?
Yeah, essentially it's a giant meteor strike will kick up material. So imagine like a dinosaur killing asteroid, like one of these giant rocks smash into the surface of Mars. Mars is actually kind of easier than Earth because it has lower gravity. And some of those rocks will be pummeled up into space so high just from that collision, they will escape Mars's gravity and fly off into deep space and potentially collide with the Earth.
It's like the creation of the moon is a similar event.
Yeah. So it's not something you expect to happen frequently, but it does sometimes happen. And we have actually quite a few meteors which we've collected. They're often found in Antarctica purely because it's easier to find them there. You have this pristine white snow, and so there's a bunch of if you call them astronomers or what exactly their profession would be labeled as, but they ride around on these skidoos, you know, or the huskies, like looking for because it's really easy to spot like a little black dot in the snow, and they scoop them up and bring them back to base, and then that's how we get a lot of our samples. So they're probably landing everywhere, but that's where it's easiest to find most of them.
I mean, what a fascinating idea to
cool
find.
Job.
Oh my goodness, like so cool. Hanging out with dogs all day looking for rocks. I mean, it's like my dream.
Let's go.
Yeah.
We need to find some meteors.
But how exciting would it be to find this little fossilized microorganism and detecting the genome and finding that it's the same as LUCA?
Yeah.
And what that would mean for us.
That's like straight out of Hollywood, right?
Oh my goodness, it's so exciting.
But it could happen any day now. It could happen that he could be the one to find that.
It is interesting to me that so few meteors strike Earth in the past, 200,000 years. Or 2,000 years rather.
Yeah.
It seems it's at least from a layperson that there's very few meteor strikes.
Yeah, I mean, certainly large ones. Yeah, I mean, we get struck by micrometeors all the time.
Mm-hmm.
So, I mean, you've probably seen a meteor shower at some point in your life, and that's meteors coming in.
Mm-hmm.
But they're so small that they burn up in the atmosphere, and they don't make their way
But
all
things
the way
like
down to the ground.
Tunguska event,
Yeah.
Things like that are so rare.
Yeah, they're once in like every few 100,000, maybe 1,000 years, a few hundred years type regularity.
Do you think they used to be more common? Is there any research that suggests that they were more frequent in our early history of Earth?
Only in deep time. I mean, if you go again to when the Earth was first forming and the Moon formed, that kind of period, so 4 billion years ago, then there was like a crap load of stuff pummeling the Earth on an almost daily basis, and that's just because there was there's only a finite pool of rocks hanging out in space, and so every time one hits the Earth, there's less of that pool left over to hit. And when the Moon and the Earth were first forming, it was chaotic. Stuff was still literally in the process of coalescing from those rocks. So yeah, I think the Earth got most of its impacts in that early period, and then things kind of settled down. There was a period called the Late Heavy Bombardment, especially around that early time, about 4.4 billion years ago, where the Earth was just being absolutely knackered with this stuff, and it would have almost certainly, even if life had got going, it probably would have extinguished it pretty quickly. So we had to really wait for that period to end before life could get a foothold and sustain. But I think what's interesting about these strikes, I mean, is obviously the dinosaur impact, the KT transition as it's called, but there's a whole bunch of mass extinctions. If you just look in the last, again, few 100 million years, I think there's 5 mass extinction events which happened. Only one of them was conclusively due to a meteor strike. Some of them are due to volcanism on the Earth. Others are due to even one is actually, I think the Ordovician one is still unknown what caused it, and some people hypothesize it could have been a gamma ray burst or a supernova from a nearby star that triggered it. But the point is, there's been a series of mass extinctions over a relatively short time, in geological time, like 100 million years or so. And yet, even though life constantly got a real battering, it never went away. And it's important to remember that life is like an infection on this planet. It's really hard to scrub it out.
Mm-hmm.
Like, even if you kill 99.9% of all living things on this Earth, within 10 million years, it's pretty much bounced back because you've left over all these ecological niches, and now life can just fill that all back up and evolve and take over again. And I kind of, I wonder if intelligence is the same way, that you could, what would happen if there was a giant meteor that knocked off most of humanity? But would it truly be able to knock off all of us? That's hard, because you've got people with their bunkers. You've got, the president with his 1 kilometer bunker or this kind of stuff. You've got Elon Musk probably with some kind of crazy lifeboat situation. You've got astronauts up in space. And so I think it's maybe, and there's parts of the world, you've got humans living in Antarctica from pole to pole.
Mm.
I think it's difficult to imagine an event that would be so catastrophic that every single pair of breeding humans would be extinguished on this Earth. And therefore, I'm fairly optimistic that even if we might end ourselves at some point, it probably won't even be anything that dramatic. It'll probably just be like slow economic decline or something like that, to be honest. I think that's the most likely end story for us. That eventually it will bounce back, and over millions of years, those creatures, which we once called humans, will look quite different, and they'll change and they'll evolve and adapt to their changing environment.
Yeah,
and so it's just a continuous story, a thread of there's lows, but it always comes back.
Right. And even if it does take out all Homo sapiens, this is not to discount chimpanzees and bonobos, and which point you just set us a little farther back.
Yeah.
And then in which case they could become intelligent given, a few 100 million years.
Yeah. And maybe these resets, it's argued these resets maybe are necessary, right? Because if you hadn't knocked off the dinosaurs, we probably wouldn't be here, right? You had to kind of clean the slate a little bit to let evolution have a reset and get going with a new direction and try something else out. And if it wasn't for that, you'd have a stagnation where you just kind of, life got stuck in a rut. Yeah. I think about that in my own life. I'm coming up to 10 years now at Columbia, and I'm like, I need a extinction level event. I need to shake up my own life a little bit. I need to shake the tree. And I'm thinking of moving to the UK for a year next year and just trying something different, because otherwise you can get stuck in ruts in your life. and evolution too, where you find yourself coming up at the same office every day doing the same thing, and you lose your creativity and your flow.
Oh, absolutely. I mean, why does every great album get made in some far off cabin somewhere in some exotic place? I think the creative evolution requires a set and setting change, certainly.
Yeah.
And I think that goes for probably all creativity, I assume.
Yeah.
And you almost wonder if evolution functions the same way.
Well, it is a creative process for sure. I mean, it's not the way our creative brains work, but it's definitely come up with very creative solutions.
Well, maybe it'll be Apophis. What do you? Can you explain Apophis and if we should be concerned about it? Are you familiar with this?
What is Apophis?
Oh my goodness, I'm sure you've heard of this.
Okay.
Christos, could you just Google Apophis asteroid?
Is this one that might hit us?
Yeah, this is 2036, I believe. It's supposed to have a near-Earth.
I think there's a bunch of these objects. I don't remember their names. Yeah, but
this is one. Again, this is sort of a colloquial name that was given to it. This is the Egyptian god of destruction or something like that. Originally, it's probably called like W56 or something. But allegedly, this is. It's going to make a near-Earth orbit in 2028, and then I think a closer one in 36.
Okay.
On Friday the 13th.
Wow. Good day.
And apparently it's like the size of the Rose Bowl.
Okay.
And it's like this massive, space debris that's going to come very close.
I assume it's not on a collision course because probably there'd be more panic about that. But there's a few of these things that pass even underneath our satellites. And that's terrifying to think about, but it happens quite frequently. I mean, the Earth is actually kind of small compared to space. Space is really big, so it's quite hard to hit. It's quite hard to hit the little Earth with these rocks. So I mean, some people say, well, we're due for one. Like we haven't had an impact for. Of kind of 65 million years ago is when the dinosaurs were knocked off. So we haven't had an impact like that for millions of years. And so you can do the calculation and say, well, roughly every 50 million years or whatever, you get impacted like that. So therefore, we're overdue for something like this to knock us off. But that's gambler's fallacy. I mean, that's like going to the casino and saying, I've lost 5 hands in a row, therefore I'm due for a win. Like it just doesn't work that way. Like every hand is a new hand. There's no logical connection to the previous hand. So, if you'd just been hit yesterday, the chance of you getting hit tomorrow is the same as it is 10 million years into the future. It doesn't evolve the probability. But yeah, on average, these things do happen. And, I hope we can build defense systems for these things. There is interest in doing that. Maybe putting you can try painting them, for instance, is an interesting idea. You can paint one side of it very shiny, like white paint, essentially. And then the radiation will reflect harder off that one side, and it can influence the motion, basically from solar radiation pressure of the object. So how we build solar sails, obviously, is pushed by solar radiation pressure. And these things are actually fairly light compared to planets. And so they can be quite significantly affected by solar radiation. And so that would be a pretty cheap method. Like you don't have to blow it up. You don't have to put rockets on it. You just literally, bomb one side of it with a big paint bomb. And that might be enough in some cases to push them off course. Oh,
wow. Armageddon would have been such a different movie.
Yeah, if they were graffiti artists.
They're go up there and just tag it a little bit. You know what I mean? Put some glue or something. But that is interesting. That idea, you're talking about these sails, which effectively you're like, these photons have mass, right?
They don't have mass. They have energy in this. They have momentum. So
I see. Okay.
Because they have momentum, that's how they push things. But they don't have any mass. Yeah.
I see. Okay. Yeah. And so because they're able to push things with energy.
Yeah.
Like I used to have when I was a little kid, I had a little it looked like a light bulb.
Yeah.
With a sort of rotating little, almost like a windmill thing inside.
Yeah, a radiometer.
A radiometer, that's what it was. And you could blast it with a laser pointer.
Yeah.
And it would spin.
Yeah.
Is this functionally the same thing?
Yeah, essentially, yeah. You might even use a laser system, in fact, to push it. So you could paint one side and then add a laser on for fun to make it even more.
It always becomes sci-fi.
Pushed.
It's so fun. Like this thing right here.
Yeah.
So you paint the asteroid and then blast with a laser and then spin it off into deep space.
Yeah, you could even spin it so fast you could break it up. Right, that's another option. So if things spin, a lot of the asteroids are spinning pretty fast. And there's a whole bunch of them which are quite close to what's called breakup speed. And these things aren't that solid. They're kind of mostly rubble piles. So they're very loosely, they're basically pebbles held together. there was actually, we had a speaker at Columbia on Wednesday who was showing us video of landing on Bennu. So Bennu's an asteroid that we've actually landed on and collected material from. And they had this arm that was going to touch the surface and basically vacuum up some material and then go away. It's just like it's called a touch and go. Just touch it and suck it off and go. But they only expected to basically scrape the surface, and they ended up plummeting 0.5 meter down because the material was so soft and so loosely held that and that's kind of crazy to think about. If you had jumped onto this thing, it'd be like quicksand. You would just like fall into this pile of pebbles and sink down into it just from your own force. And so, we have the idea that these are like solid rocks, I think, quite often in our minds, but they're actually pretty tenuously held together. At least some of them are solid, but there's a lot of them which are tenuous. And then in those cases, if it's pretty tenuous, it doesn't take much. You could just spin it up and the whole thing will just disintegrate apart.
Wow.
That'd be a really nice way to get rid of some of those things.
Oh, fascinating. Okay. Is there I'm curious about Planet 9.
Yeah.
We had talked about this briefly before, and it seems, again, I know virtually nothing, but I've seen some debate that it's sort of this abandoned idea, or that there is still a lot of like legitimate, research into this notion of Planet 9. Can you describe what this is and why it matters for astronomy?
Yeah, it's a fascinating idea. So it's a bit of a real shtick to Pluto to call it Planet 9, I think.
Right?
So some people call it Planet X instead of Planet 9. But the idea is that there could be, and I mean, why not? We only discovered Pluto in the 1930s, so how do we know there's not another planet even further out? I think Pluto is about 100-ish times the distance from the Earth and the Sun further away from us. This would be 500 times further away. So it would be, we call the distance between the Earth and the Sun an AU. That's our unit of measure. It's about 100 billion miles. And this would be 500 times that further out in the outer solar system. So really, really far out. And that's kind of the distance where I think Voyager 1 and Voyager 2 are right now, sort of the outskirts of the edge of the solar system.
Oh, wow.
So this thing would be pretty massive if it was real. It's hypothesized to be around about sort of 10 Earth masses. And the evidence for it is indirect. So I think this is why there's controversy about it. So essentially one of my colleagues, and I love the dude, Konstantin Batygin, he's a really nice, beautiful guy. And he's a brilliant physicist. And him and Mike Brown, an astronomer at Caltech, noticed that if you look at the orbits of many objects in the outer solar system, and these are things like Pluto and other things like that, there's Sedna, Makemake, there's a whole bunch of these small objects out there. If you look at their orbits, they seem to coalesce. They seem to be aligned to each other, which is kind of suspicious. Like, why are all these orbits kind of shepherded into the same shape? And so they suggested that there must be a mass. That image, the fifth one along, that one kind of shows it. So you got those orbits there, which all seem to be preferentially facing the left. You see that? They're all kind of pointing in the same direction. And so they suggested that that's just pretty unlikely to happen by chance. There must be something causing that to happen. And one explanation would be there was a mass on the outside called Planet 9, they called it, that would be responsible for this. It seems indirect, but that's the same way that Neptune was discovered. Neptune was also found by the wobbles it causes on other orbits, in particular Uranus. So when you look at Uranus's orbit, it's not quite following the strict laws of Newtonian gravity. There's some perturbations there. And there was a French astronomer, Leverrier, who calculated that implies there must be another planet. And he predicted where Neptune was to within like a degree precision, like on the sky. Like he predicted exactly pretty much where it should be. And then the astronomers went ahead and detected it like exactly where he said it should be. So that was 150 years ago we did that. So it's kind of using that same principle of like, let's use the math of the orbits to figure out what else must be out there. And if you believe that, there is a lot of evidence that there should be another planet. The controversy though is that no one can find it. So we've looked really, and it's a big planet, 10 Earth masses. You should really see something especially in the infrared. It'd be pretty cold, but it should still produce a tiny bit of infrared. And we've been surveying the sky very deeply. And I think now they've ruled out something like 75, 80% of the sky. They've looked in every position where it should be. And basically 80% of those positions, they don't see the planet, and they should see the planet. And there's like a little bit of space left. And essentially, the only place where it could be now would be that it's called its apastron. I'll just say apastron. Apohelion is the correct word around the sun. So that's it's in an elliptical orbit around the sun. And so there's the perihelion when it's at closest approach to the sun, and the apohelion when it's at furthest approach from the sun. And if it was close, obviously it'd be easy to find because it's nearby to us. And the only place it could be now is right on the edge of that wide orbit at the aphelion position. So some people are saying, like, it's a little bit contrived that you're saying there's a planet there, but it just happens to be in the one place where we can't see it. It's a little bit convenient, right, that we can't see it. But it does explain all of this shepherding stuff of these orbits and other mysteries as well. For instance, there's a slight twist of the sun's tilt. So the sun is tilted by about 6 degrees compared to the planets. And that has been a long mystery. Like, why is the sun tilted over like that? And Planet 9 could also explain that. So it can actually explain a few different like problems in the solar system. I remember Konstantin Batygin, he's a great guy. He's a rocker. He has a rock band. I think his band's called Seven Sisters, I think. He's the lead singer and the lead guitarist for them. And he has another astronomer who plays, I think, rhythm or something with him in the band. And they're pretty heavy. They're a really fun band to check out. And he's a surfer. He's like a really like super cool guy. I really love hanging out with him. And I remember I said to him, I showed him like evidence of an exomoon we had, and it was, I think, 5 sigma confidence, which basically means like 99.99999% or something. And I said, what do you think about this? I'm like 50-50 whether this is real or not. And he said, dude, I would like totally believe that was real. And I was like, well, how much do you believe you're Planet 9? Like, do you really think it's there or not? And he said, I'm 99% sure it's real.
Wow.
And I said, how could you be, I didn't understand it because as an astronomer, I'm always doubtful of my own stuff. Like anything, it's like anything I do, I'm like super skeptical about, like I probably made a mistake or something. And he was like, no, I'm 99% sure this planet is really there out in the outskirts of the solar system. I guess the nice thing is it's completely testable. And so one way or the other, we will find out. And it's certainly would be a big deal because for 2 things, I think. One, it would be a super Earth. We don't have a super Earth in the solar system, at least unless this planet's real. And yet super Earths are the most common planet in the universe, as far as we can tell. The super Earth's everywhere. When you look at other solar systems, you always see planets that are about this size and this mass. They're just everywhere. But we don't seem to have one.
When you say super Earth,
yeah,
you're meaning what exactly?
I mean a planet that's about twice the size of the Earth and about 10 times as heavy.
And similar sort of chemical makeup?
We're not sure. We're not sure of the chemistry.
Okay.
We only know really the radius and the mass. That's all we can really tell. But we see that planet all over the place. It's just it's the most common type of planet in the whole universe, as far as we can tell. And yet the solar system does not have one. So that is, to the solar system's uniqueness, that seems interesting. But if Planet 9 is real, that's our super Earth. It's just sat out really, really far away from the sun. So that maybe resolves one mystery. And then it'd be cool because if it's real, we could fly a spacecraft there and we could actually see what a super Earth looks like up close and personal, which would be nice because otherwise there's no way to do that for these, obviously, super Earths around other stars. Also, it could be an interstellar kind of refueling point, right? Because this is really far out on the outskirts of the solar system. And so it could potentially it should probably have a whole system of moons if it's out there. So you can imagine that being a really great place for an interstellar mission to like pause, refuel, take a break before it goes on to the next waypoint, as long as it's in the right direction, because it's obviously moving around. But I think it'd be kind of fun as a deep, deep space probe. That's my own sci-fi reason why I like it. But I think it solves a lot of mysteries from the formation perspective as well.
Do we have any conjecture as to when it'll be orbiting closer to the sun based off of the other planetary orbits?
Yeah, I mean, if it's at its furthest approach now, I mean, eventually it has to come back around, but its orbit is so wide, I think it's like 100,000 years, its orbital period.
So we'd have to wait till then.
Yeah, I'm not waiting that long.
We got stuff to do.
Yeah, too busy for that. So I don't think we'll have to wait that long. I think, as we mentioned this Vera Rubin telescope coming up, that is thought to, again, nail that 80% number down to like 99.5% or something. So I think that'll pretty conclusively either find it or not find it.
Is the search for Planet X, when that telescope comes online, a high priority, or do you think that'll be shelved until like 2028 or something?
You mean using it to search for Planet 9?
Correct.
Yeah, it won't even be, that's not even really an issue because no one gets to go to the telescope. It's not like a conventional telescope where you go to it, you point at what you want to look at, and you do your science. It's a survey telescope. So that means that it has a pre-programmed set of observations it's going to do, and that's sort of set in stone, essentially. I mean, obviously there's committees that will decide exactly how they schedule it, but it's trying to basically create a video of the sky, which is pretty cool. It wants to it's going to look at one patch of the sky, take an image, I think for like 30 seconds. I think it takes two 15-second images, and then it shifts to another field and does that again. So it just is constantly moving around, and after about an hour or so, it's tiled the entire sky, and then it goes back to the first position and does that again. So we will actually have a 4K, even higher than 4K, super high resolution movie of the sky with about an hour frame rate, something like that.
So we could have an answer about...
it's going to do it whatever, yeah. The point is it's looking it's looking all over the sky, and it will, if Planet 9 is there, it's somewhere in the sky, so it will find it.
By next year, potentially.
Yeah. I mean, I don't know if it'll be as soon as next year, because it probably needs to build up the data. It's a 10-year survey.
I see.
So I imagine it would take a couple of years at least to get enough data to have a definitive answer. But I think it's soon. Yeah, I don't think you're going to be waiting 100,000 years to get an answer. That's for sure.
Right.
Yeah.
Oh, that's so exciting. Yeah. Okay, now let's get into the more metaphysical, the sort of black holes, time travel, dilation, all this sort of crazy sci-fi stuff.
Sure, yeah.
But really quick, we're going to take a break. If anyone has any questions for Dr. Kipping, please drop them in the comments, specifically relating to this topic would be awesome. And we'll be right back in a second after a word from our wonderful sponsors that make this show possible. What's up, guys? We're going to take a break really quick because it's 2024, and it's time to talk about something important. When you are seriously hurt, your injury could be worth millions. Yes. That's right. The world is a crazy place, and one person's negligence can result in another's settlement. And that's why I got to talk to you about Morgan & Morgan. Morgan & Morgan is America's largest injury law firm. They have over 100 offices nationwide and over 1,000 lawyers. Yes, these are the big boys. You know them, you see their billboards all over the world. If you ever drove down I-90 from Florida to New York, I'm telling you, you've seen the billboards, all right? Have you ever watched a UFC fight? You've seen them right on the banner. I'm telling you, these are the biggest guys in the game, all right? With over $20 billion recovered for over 500,000 clients, Morgan & Morgan has a proven track record of fighting to get you full and fair compensation. The annoying thing with most attorneys is that in order to submit a claim, you got to call them up, you got to talk to their people, you got to go back and forth on emails, you got to hope that they see it. They might charge you just to even look at their claim. Here's the cool thing with Morgan & Morgan. With 8 clicks or less, you can submit a claim, and one of their licensed attorneys will take a look at it and get back to you. It's that easy. It's like ordering something off Amazon. It's just a couple clicks. You can submit your claim very easily and cheap. Yeah, how about $0? That's how much it costs to submit a claim with Morgan & Morgan. Extremely easy, no fee required. So, if you are ever injured, you can go check out Morgan & Morgan. Their fee is free unless they win. That's right, unless they win for you. Unless they fight and get you compensation, you're not paying a single dollar. That's a pretty good deal. So, for more information, go to forthepeople.com/Gagnon. That's correct, forthepeople.com/Gagnon, or dial pound law, that's pound 529 from your cell phone. That's for the people, forthepeople.com/Gagnon, or dial pound law, pound 529 from your cell phone. This is a paid advertisement. Now let's get back to the show after this short disclaimer. What's up, guys? We're going to take a break really quick because I got to tell you about an amazing service known as Blue Chew. That's right. Blue Chew is a service that basically delivers this chewable tablet to your door whenever you want, once a week, once a month. I don't even know if they could do it that frequently, but they'll send it right to your door. You don't have to go to the doctor and have some awkward conversation with some guy in a lab coat, some dude that's judging you, probably, if I had to guess. With Blue Chew, it's super discreet. The packaging is discreet. It's just a couple questions on their website, and they will send you chewable tablets that have basically the same active ingredients as like a Viagra or a Cialis, but at the fraction of the cost and in a chewable form. It's great. It truly is. I mean, one time I was in the woods and we were cold and it was raining, and I pitched a tent with the help of Blue Chew, and everyone gathered under it, and we were safe, and it saved me and a lot of lonely people. So if you're interested in Blue Chew, Here's how you get it. You're going to go to bluechew.com and use the promo code Gagnon. That's right, Gagnon. It's kind of funny, Gagnon as the promo code. I don't know why exactly, but it is funny. And you're going to receive your first month for free. That's right, bluechew.com. Use the promo code Gagnon. Check it out. Blue Chew. Let's get back to the show. And we're back with the amazing Dr. Kipping. Christos, were there any specific questions that popped up in the chat that you saw that were compelling? Okay, cool. Okay, let's look here. From Wedge Smith, does he think the Bell Island boom was an astronomical atmospheric event or something else? Are you familiar with that?
No, I don't even know what that is.
The Bell Island boom. I'm not sure.
No idea. Sorry, pass.
Sorry. Okay, I want to ask you about black holes.
Yeah, let's do it.
Okay. Is there anything that you've seen as of late as far as, sort of the black hole research event horizon, insanity that goes on that you found particularly compelling that you've looked into, or any of your colleagues that have written papers that you've looked at to say like, oh, the research on black holes is like pushing forward in a significant way?
Yeah. Yeah, I think black holes are totally fascinating for so many reasons. But to physicists, one of the most interesting things is they seem to be a bridge between the large scale, the general relativity, the cosmological models that we have of the universe, and the micro scale that the quantum theory kind of addresses. And they seem to be a region of space-time where these two theories kind of come into tension with each other in a real way. And so a lot of the progress that we've been making, there's been some observational progress. We've been detecting merging black holes with LIGO, which is using gravitational waves, which is amazing, by the way, that we can, again, this is like ridiculous engineering accomplishment that you can detect space itself. Like there is a black hole probably merging somewhere in the distant universe right now that creates a ripple. That ripple passes through us, me and you right now, Mark, and it is stretching physically the space between us by a fraction of a proton width. That's how much this space is moving by, a tiny, tiny amount. And yet we can detect that. Right? We have laser interferometry that can detect things that space itself warp in by a fraction of a proton width. Is ridiculous. And then we can figure out like where that happened. We can triangulate them because we have several of these interferometers now. We can locate where the object happened. And even now, for some of those mergers, we've seen not only the gravitational wave ripple through space-time, but when we look to that region where we think it happened, we see a flash of light happen as well. That's called the electromagnetic counterpart. That doesn't happen for black holes merging, but it happens for neutron stars when they hit each other. So neutron stars, again, they're so massive that when they collide, they create these gravitational ripples. But because they're physical objects, they smash into each other, you get a big explosion as well. So there's some amazing observational work happening there. There's many things observationally we can't do. So I think one of the things we'd love to detect is Hawking radiation, for instance, of a black hole. And that just seems like it's just never realistically going to happen.
And what exactly is that?
So this is something which happens around a black hole that Stephen Hawking predicted. And essentially, if you imagine like the simple explanation, you can get into sort of the wave theory of it, but the simple explanation is if you imagine a pair of particles that are born on the event horizon, which happens in space all the time. There's these vacuum fluctuations where a particle and its antiparticle just pop up into existence. This is allowed by Heisenberg's uncertainty principle in quantum theory. It says this should just be happening all over the place. And one of them can kind of fall into the black hole and the other one can escape if they're just sort of sandwiched around the event horizon. And so a particle basically flies off from the black hole. It escapes. And so that means overall the black hole must be losing energy, it's radiating. And so that's called Hawking radiation, this quantum effect. I think this is where Stephen Hawking made such a big difference, was realizing that a quantum level effect should influence the evolution of a black hole, which, a macroscopic object, which normally quantum effects don't really affect macroscopic objects. But even though this is a very, very small effect, I mean, we're talking about a radiation level that's so tiny we could never detect it with our telescopes. It will, over trillions of years, even longer than that, cause these black holes to shrink in size. And so one of the fundamental insights that Hawking had is that black holes don't live forever, that they eventually evaporate away due to this radiation process. And actually, the efficiency of it gets greater and greater the smaller the black hole gets. So for a large black hole, there's very little Hawking radiation coming off it. And curiously, as it gets smaller and smaller, this effect scales up. And it turns out they kind of like almost have like a micro explosion in their last moments as they turn to a micro black hole and eventually just disappear altogether. So obviously the universe is not old enough to have seen any of those things. And so that's sort of the world of theory, but we think it should happen. People have created computer simulations of these things, it seems to agree. We've even created sonic versions of black holes where you can create, instead of using light, you use sound waves, and you create like an acoustic black hole in the lab. And you actually see with these acoustic black holes, the same Hawking radiation come off them, verifying his original predictions. So it's like an analogy. It's not like a real black hole. It's like an analogous version of it, but in a physical system. And it kind of establishes that his insight was essentially correct. So that's the closest we can do to Hawking radiation.
An acoustic black hole.
Yeah, it's so cool. It's so ingenious of an experimental setup, I think, to have pulled that off.
I mean, what does that even look like? Like the mechanisms to create an acoustic black hole?
I think what they use is, again, this is not my field of expertise, but I think they use, they propagate waves through a medium, and you essentially have regions where waves can't catch up because of the sound speed through the medium to a certain zone. And so that region is essentially like your black hole because nothing can ever kind of enter this zone. And so that kind of creates an analogy. It's not exactly a black hole, but it's an analogy to sort of the behavior of what you might expect, these kind of strong singularities that occur in the acoustic space versus light space or gravitational space. So that's kind of the closest we get in the lab. But I think on the theory side, what's really interesting with black holes is this kind of stuff about the holographic principle. We chatted about this a little bit before we came on the air. And the consequences of, again, sort of what would happen, what happens to the information essentially that goes into a black hole. So if I took a textbook and there's lots of information embedded within that textbook, but it could even be anything, it could just be a rock. Even that rock has information, which is the quantum numbers embedded within it. You throw it into that black hole, the information is seemingly destroyed. It just disappears. And that violates a fundamental core philosophy essentially of quantum theory, which is reversibility. So nothing can truly, wave functions don't end. They extend from the beginning of the universe to the end of the universe, and they can't just completely disappear. So that information must, in principle, be preserved somewhere. And for a long time, we were okay with just sort of dismissing this problem because, like, if it falls into the black hole, that's almost like a separate universe or whatever, who cares? But then when Hawking said, no, stuff gets out of it, the thing eventually escapes. Everything eventually escapes from the black hole. But then what happened to the information? Does the Hawking radiation carry away the information? If we collected the Hawking radiation up, could we eventually reconstruct the book? In the same way, if I threw a book into a fire, it gets, turns into ash and smoke. In principle, if I collected up all that smoke and ash, I should be able to reconstruct the words on that page. I mean, in practice, you can never do this.
Right.
But in principle, the information is encoded within the motion of each one of those smoke particles. And so the idea is, could the Hawking radiation encode that information? But that causes its own headaches in quantum theory. And in particular, remember I described how these Hawking particles are produced at the event horizon. That's where they're produced. But the book fell into the singularity. It fell past the event horizon, right? So it's deep down. So how does the information that's deep down in the black hole have anything to do with information which is leaking out on the event horizon? Those are two spatially separate places. So this is the whole conundrum of what's called the black hole information paradox. Like, does information truly get destroyed and therefore there's something wrong with our understanding of quantum theory? Or is somehow the information that falls deep in somehow coupling to the information on the outside, on the event horizon? And one idea is that some of my colleagues, like Jana Levin, who was on my podcast talking about this, was a big proponent of, was the idea of some kind of entanglement, quantum entanglement happening between them, or perhaps even micro wormholes essentially forming inside the black hole that allow information from the core to reach its way back to the event horizon and then escape out into space. And that seems a little bit hard to believe, But this is why black holes are so fascinating, because they force you to marry two theories, which normally we can ignore. We can normally ignore the problems between them, but in black holes, you can't ignore it. Like you can't understand what's going on with the Hawking radiation unless you can connect it to the deep interior. And that is advancing theoretical physics, I think, in a way that I don't think any other object is forcing us to confront those two dilemmas, those two worlds.
Now, you're describing the black holes as evaporating. Is this different than a black hole collapsing?
Yeah, it's the opposite. It's an explosion rather than implosion.
I see.
Essentially. I mean, it in physical size, it shrinks, right? As it evaporates, it gets smaller and smaller, but it is emitting radiation as it does so. So it's exploding in terms of losing energy, flying out into space. If you accelerated, I mean, if you could flick time forward on fast forward, you'd have a black hole. And obviously, at the moment, the universe is a pretty busy place. So black holes are generally growing larger over time because stuff falls into them and accumulates more mass. But eventually, let's say the universe gets quiescent and everything's done, there's no more accretion. After that point, if you fast forwarded, the black hole would just shrink and shrink and shrink, and it would just be bright. It would just be just shining light out as it emits all that radiation back into space.
Oh, wow.
And so then eventually, if you go really far forward into the universe, there's nothing left, right? We thought for a while maybe the black holes would be the last thing that was left in the universe. But even those evaporate, and even matter eventually evaporates. So even a planet that had nothing to do with a black hole was nice and distant, safe from a black hole. Even the atoms on a planet will eventually evaporate away, because on this desk, the atoms inside your body, they all have kinetic energy. They all have wobbles and motions. Even if it's very close to absolute zero, it will still be moving a little bit. And now and again, with enough kind of monkeys in a typewriter, enough rolls of the dice, now and again it will fortuitously have enough energy to escape and basically boil off into space. And eventually all objects will do that. They'll basically boil off over, this is like vast, vast periods of time. But then you end up with a situation where planets have boiled off, stars have boiled off, even the black holes have evaporated. And so all you're left with is just this homogeneous bath of very, very, very cold radiation that's left in the universe. And that's called essentially the heat death, towards the heat death of the universe.
Wow.
So it's a dark future.
Have we seen in our timeline, we haven't seen any black holes fully evaporate?
No, we haven't seen this process occur because it occurs on such vast timescales. So this is purely a prediction of Stephen Hawking's theory and other physicists. But yeah, it's purely a predictive effect. This should happen.
But have we seen them evaporating in any capacity, like shrinking? Or is that all theoretical?
No, I mean, there was an idea that maybe with the LHC, the Large Hadron Collider, and certain particle colliders, and maybe at Fermilab, this could happen. You could, with high enough energy, create a micro black hole. It was actually a cause for concern. People were worried about that. They were like, well, maybe this micro black hole might suck up the whole Earth or something, right? That would be a pretty bad day for the Earth. But the problem is they just can't last long enough, at least unless Hawking's wrong, which is possible. But according to Hawking, the smaller the black hole is, the faster it evaporates. And so if you create a micro black hole, it evaporates within like a femtosecond, like 10 to the power of minus 15 seconds or something. So these things just are very transient. Unless you were able to make something that was like an Earth mass worth of black hole, then it would be stable for a long time. But obviously, these particle accelerators are dealing with nowhere near that amount of energy. So
the black holes that are created in deep space start off at a size large enough to sustain and grow.
Yeah, I mean, it's an interesting question actually how black holes form. We think most black holes probably form from the collapse of very massive stars. The sun would not collapse into a black hole. It's not massive enough to do that. It will just become a white dwarf as it ages and then eventually peter out to a black dwarf. So just basically that would be the core of the sun. It will just kind of cool down over time. If a star is more massive than that, say about sort of a few solar masses, a few times the mass of the sun, then it will form a neutron star, which is basically where the matter is compressed so much that it forms a giant atom. So the normal forces that stop atoms, the electromagnetic forces that stop atoms from touching each other and forcing them together are overwhelmed, and you basically fuse everything into one giant atom, an atomic nucleus, essentially, which is called a neutron star. So that could be something that's like 10 kilometers across and like the size of Manhattan, essentially.
The atom itself?
Yeah, an atomic nucleus that's the size of Manhattan and is the mass of a star. Yeah, so that's a neutron star. They're pretty bizarre. They are, I think, clearly the most exotic states of matter we know of in the universe. I think that's true to say. There is nothing more extreme in terms of a matter state than what happens in a neutron star. Because a black hole, which you might think is more extreme, is not matter. It's not matter. It's a region of space-time. That's all it is. A black hole, you can't even really talk about the matter inside it because it's inaccessible. It's behind the event horizon. So all a black hole really is that stage where even the nuclear forces, which are propping up this neutron star, that's what's stopping it from collapsing further is nuclear forces within it. Even those are overwhelmed, and gravity is so strong it takes over and crunches it all the way down into this singularity eventually at the bottom of the black hole. So those black holes are very strange objects, but they're not doesn't maybe make sense to think of them as a ensemble of matter. You can even form black holes in principle from laser beams, right? From energy. You could shine a whole bunch of lasers in one spot and there'd just be so many photons there. Photons themselves actually also have a gravitational influence. And so you could actually have enough energy density in one place. It's called a Kugelblitz, that you could create a black hole just from energy. And another final way you could make black holes, that would be an artificial method. A civilization, maybe super advanced, could do that. Or we could do it in a particle accelerator. You can have stars die. And a third way is called a primordial black hole, which again is speculative. We don't know if these things exist or not. But soon after the Big Bang, there was so much mass and so much energy lurking around. The universe was very small. It was very, very dense. It was so dense that if one region was just slightly denser than another region, it might be enough to collapse into a black hole directly. So this, again, would not be collapsing from matter because there was no atoms or protons or anything at that point. It was just a soup of energy. And we don't even know exactly what the particles were at that point. But whatever that energy was, that energy field, could have been so dense that it could have immediately collapsed into a series of primordial black holes. And those black holes could be quite small. So it's the size of the Earth even, or the mass of the Earth. They could be black holes that small. And so those could be evaporating because, remember, the smaller the black hole, the faster it evaporates. And it was even proposed, coming back to Planet 9, one author suggested that Planet 9 could be a primordial black hole. That would actually kind of fit a lot of the reasons why we don't detect it. So it does all the gravitational shepherding that a planet would do, has the same mass as a planet. The reason why we can't detect it is because it's a tiny black hole, and it would be about the size of a bowling ball, the event horizon. So it's kind of wild. You can actually hold it in your hand. You won't want to put your hands on it.
Yeah, I'm not getting close to that. That's a setup.
But this would be a bowling ball-sized black hole on the outskirts of the solar system. That plausibly matches all the observations of Planet 9 thus far, and would be one of these relics of what happened just immediately after the Big Bang, essentially.
Yeah, I guess that's what I'm curious is it possible that there are black holes very close to us that are being created and then evaporating quickly that technically we could detect, we're just not seeing them because they're either happening so fast or they're undetectable?
Yeah, I think it's hard to imagine a micro black hole forming spontaneously in space because to form a micro black hole, you have to have a very, very large amount of energy in one place simultaneously. And by Heisenberg's uncertainty principle, you can borrow energy for a short amount of time. And so things do pop up in and out of existence, but it's kind of like, it's much easier to borrow a small amount of energy than a large amount of energy. And so the probability of randomly forming a black hole in space would be finite, but it would be a very, 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 very small number. So I think it's, I don't know if anyone's made that calculation, but my feeling would be that would be such a small probability that it's not something we're likely to see.
If Planet 10, quote unquote, is a black hole in our solar system, what are the implications of that? How does that change our understanding of the universe if we're able to interact with a black hole in relatively, close proximity to Earth?
Yeah, it'd be wild. I mean, black holes are kind of amazing because they're essentially systems where you can convert mass into energy in a pretty pure way. So, in Star Trek, they have the ability to do this transfer where you can basically have a replicator, right, which can like turn energy directly into matter, and then they can also recycle the matter back into energy. You can just like beam it back up, essentially, in a little teleporter. And a black hole has the ability to do that process. There's these, for instance, you could throw something into the black hole, and it would be disintegrated, and it forms these jets, which is kind of normal to the spin of the black hole. And those jets, it's been shown, have a very, very high efficiency of converting the matter into energy. So you could use it as a trash dump, right? So you could take your nuclear waste or whatever trash you have, throw it into it, and turn it into a gigantic amount of energy by E equals mc squared. Even a single gram of mass produces like astronomical amounts of energy. You could power your entire civilization with just like a pebble thrown into the black hole. So it'd be incredibly useful if we had one in our neighborhood. So I think it would be, and if people worry about like the threat of a black hole, but there'd actually be, if you think about what an advanced civilization would, how it would want to power its civilization, it might actually seek black holes. And so Carl Sagan often speculated that there's a supermassive black hole in the center of the galaxy, called Sagittarius A star. He suggested that advanced civilizations would migrate there because it's the ultimate power plant. If you want to power your civilization, that is the most efficient and elegant way to do so. And so maybe we should be focusing our search efforts in those black hole regions, in fact.
And when you talked about a refueling station,
yeah,
I mean, a black hole over there would be pretty nice, right?
Right. Yeah, and I had a paper a few years ago called the Halo Drive, which is a propulsion system which is based off black holes as well. So this uses essentially the spin of the black hole. If a black hole is spinning or it's in a pair where they're rotating around each other, you can extract that energy. These are called Penrose type processes, named after the theoretical physicist Penrose, who first showed that this was possible. But there's a whole class of these types of energy extraction schemes now. My scheme was a little bit different to Penrose's original idea, and it uses a laser beam. So you basically fire a laser beam around the event horizon, just miss it. You just go off to the side. And as it skirts around, you go in the direction of the spin. So if, let's say this, it's going clockwise, you go from the left and you come round and you get accelerated because the black hole drags space-time around with it. So this is called frame dragging. Literally, it's like a merry-go-round of space-time. It pulls space-time around. And so the light beam wants to get accelerated, but of course light can't get accelerated. It always has to travel the speed of light. So instead it gets blue shifted. So it comes back to you with more energy than it began with. And therefore, the black hole loses that corresponding amount of energy. So the black hole itself, you steal the energy off the black hole to do it.
And the photons are able to escape the black holes
as long as they don't go into the event horizon.
As long as it's around it.
Yeah, because the event horizon is by definition the radius at which light cannot escape. So anything exterior to that, light can in principle escape. Depends on there is also an ergosphere where light can actually follow an orbit around. So actually gets kind of trapped just like a planet can orbit a black hole.
Oh, wow.
A light beam can orbit a black hole. So you want to kind of choose just the right geometry. So you go as close as you can, essentially. And there's these tracks, they're called geodesics, as we talked about earlier, and they're called boomerang geodesics that was solved for in a previous paper, not by myself, but another physicist. But we exploit this effect, these boomerang geodesics, where light, it's like a mirror. Light starts from one place and it comes exactly back to where it began.
Oh, wow.
And so you can calculate exactly what the boomerang geodesic is. You fire your light along it and you're guaranteed for it to mirror. So you can actually see yourself in a mirror, essentially, if you followed this exact beam of light.
Now, wouldn't it destabilize the black hole?
It wouldn't destabilize it, it would de-spin it. So just, a black hole, it's how you would ever rip apart a black hole is an interesting question. They're pretty solid, not solid literally, but they're pretty difficult to imagine ripping apart a black hole.
But if you're stealing energy from it.
Yeah, you're going to de-spin it, essentially. So.
And what would that do if you de-spun it?
And nothing really. Eventually you just run out of spin. So then you can't use it as a battery anymore. But it's like a flywheel. A flywheel is an energy storage system where you basically take, a propeller or something and you just spin it really fast. And as long as there's no friction, the solid arm will keep rotating and it's storing kinetic energy. And then you can, at will, tap that energy out of the flywheel. So it's essentially a giant battery, the flywheel.
Because it doesn't affect the density of the black hole.
No, it doesn't affect the density or the mass. Yeah, only affects the spin. That's it.
Oh, wow.
Yeah.
And so once it stops spinning, it's just no longer...
There's no energy to extract. But these things have I mean, some of these things are spinning close to the speed of light in terms of their rotation speeds. And so they have almost as much energy. Some of them have comparable amounts of energy in spin energy as they have in actually gravitational mass energy. They have like huge amounts of spin energy, which isn't surprising because as something collapses down, think about like an ice skater, like tucking its legs in, they tend to spin up. And so it's generally expected that as you collapse a black hole from a dead star, it will spin up very, very, very fast. Some of the neutron stars that we've detected, which are not as extreme as a black hole, they are spinning at like blender speeds, like once per millisecond. So every millisecond, the entire Manhattan-sized star will do a full rotation every millisecond. That's about as fast as your blender. So that's got a millisecond pulsar. We know about the stars that do that. So black holes are presumably spinning even faster than that.
Do they all spin the same direction?
No. It will depend on the geometry of the solar system from which it collapsed in. Yeah.
Oh wow. Oh, it's so fascinating. I mean, it just like breaks your brain to even consider like the implications of the black hole. But if we can get some energy from it,
I think they could be very useful. And I was speculating in this paper that if you were an advanced civilization, this is a highway system. Every black hole is like an EV charging point essentially, that you would hit it, you'd get your boost, and you go to the next one, you get your boost. And so they would form like a network, and every point you would get another speed boost of about 10-20% the speed of light. So you can very quickly navigate the entire galaxy using your network of black holes, which is interesting then to ask, like, maybe if this was true, if a civilization was doing this, then we should see that the spins of black holes were being eroded, right? So you would notice that. You would notice that there were certain perhaps preferential directions, maybe radial directions in and out the galaxy, where there was a sequence of black holes that seemed to all have lost their spin. And then the rest of the black holes seem to have the normal amount of spin. And so you'd be like, that looks like a pathway maybe that somebody is taking, like a highway system where people are leaving trash on the sideway or something. You could look for the same kind of signatures.
And have we found anything? Is it even
I think
measurable?
It is just about measurable from gravitational waves using the mergers. But for an isolated black hole, I don't think we have a way of measuring the spin directly.
Oh, wow. Okay. And I think in just the last couple minutes that we have, and again, I really appreciate your time. This is so fun. I think we'd be remiss not to speak about dark matter.
Yeah.
You had mentioned before that we got to talk about dark matter.
Yeah, it's a fascinating topic. Yeah.
What is the current bleeding edge of dark matter research, and what are the implications, I guess, going forward that people should be aware of?
Yeah, I mean, dark matter is a massive topic. It's actually one of the things I'm trying to make a huge video on at the moment. And it's really daunting to make a video on this topic because there is so much to say. There are folks looking for dark matter in particle detectors, building mines deep underground to try and detect what may be candidates of dark matter. So far, they keep turning up short, and some people are very critical of those efforts, saying that this is, a waste of money to keep doing this. But again, kind of like the bathtub scenario, there's still like a vast amount of parameter space because it's the unknown. So the unknown is almost infinite in terms of the range of parameters this thing could potentially have. On the other hand, we have a huge amount of evidence for dark matter's existence from astronomy. So again, we've seen like this lensing event that we looked at earlier, the Einstein cross, things like this. These are all clear evidence of some kind of mass, and it's mass which is largely transparent. And that's really what we mean by dark matter. It's just transparent stuff that lenses light. So I think some of the most interesting state-of-the-art things I've seen happening with this is trying to finally conclude whether dark matter is real, or whether there's an alternative theory of gravity which might be able to resolve this without the need for dark matter. I think some people are uncomfortable with just inventing dark matter. I'm not as uncomfortable with that just because, like, why should we expect all of our senses to detect everything? Like, that just seems to me a little bit arrogant. Like, if I can't see it, therefore it doesn't exist. Like, there's a lot of stuff you can't see that exists in the universe. Like, why would you expect that to be true? It seems an arrogant position to have. But regardless, I think the most interesting questions I've seen tackling this competition between these two models has been looking at binary star systems. So there's a telescope called Gaia that the Europeans launched about 10 years ago now. And it's been measuring the positions and velocities of stars very, very precisely for hundreds of thousands, millions, even billions of stars, in fact. And an interesting question is if you look at very, very widely separated binary star systems, they're so widely separated that if the alternative theory of gravity is correct, this Mond theory, as it's often called, modified Newtonian gravity or modified Newtonian dynamics, then you should actually see it in the motion of these binaries. And it was actually claimed. So there was a Gaia paper that looked at the motion of these binaries and said, I think the first paper said, like, we can't really tell the difference. Both theories look compatible, either Einstein's theory or this Mond theory. And then a subsequent paper came out that I think said, actually, no, Mond is preferred. Mond actually does a better job of explaining these binaries than the normal gravity does. And then a third paper came out after that, which went the other way and said, no, this guy made a mistake. So there's a lot of heat on this area right now. There's a lot of back and forth in the literature. And I think we're expecting, with the new data release that we have coming up pretty soon from Gaia, I think next year it's coming out, it should resolve this question fairly conclusively as to whether wide binaries are consistent with Einstein's theory of gravity or whether they're consistent with this modified theory. And that's obviously going to be a really important test of whether dark matter is real or not, because if modified gravity is necessary to explain their motions, then that at least proves that doesn't mean dark matter is totally absent. There might be some dark matter, but maybe a lot of what we thought was dark matter was not actually dark matter, and it was just modified theory. But yeah, my bet is that dark matter will win out, because it explains so many observations at this point, including like the lensing we've seen, tidal streams around the Milky Way, for instance. So it explains like a vast amount of observations, but it's definitely something to stay tuned to. And I think it's fair and healthy to have a degree of skepticism about it. But I'd say just be open-minded about both possibilities. Like, don't put yourself in one boat where you're saying it's going to be this or it's going to be that. Science is not like that. You don't make, a hunch. You collect data, you see what the observations say, and you adapt your worldview to what comes in. I think we're in a society and a culture that almost penalizes people for doing that. Like, changing your viewpoint is almost, seen as a character flaw. But in science, that is what it's all about. It's adapting your worldview and your perspective based off new observations and new data. And I think this is a really fun example where we're pushing against different ideas, and we should all remain open-minded to what the answer will be.
And what is the major delineation between Mond's theory and Einstein's theory? Is there a simple-ish definition?
It's pretty simple. It's basically saying that as you get really, it's all to do with accelerations. So gravity creates an acceleration, and that wants things to accelerate towards the mass. And when you're very far away, those accelerations get very weak. And normally we would expect that the acceleration drops off as basically distance squared with both Newtonian physics and Einstein's physics. And modified Newtonian theory says actually it doesn't drop off as distance squared. It drops off as distance squared up to a certain distance or a certain acceleration technically. And then after that point, it gets weaker. And then it stops, and then it starts dropping off as 1 over distance rather than 1 over distance squared. So in other words, gravity is stronger at large distances than you would expect. Because if I go twice the distance, Newton would say the force gets 4 times smaller. Mm-hmm. Whereas if I go twice the distance and it's 1 over distance scaling, it would only get half as small. So they're basically saying like it goes as that 1 over squared scaling up to a certain point, and then beyond that it goes as 1 over distance.
I see.
So gravity is stronger than you would expect at those very wide distances. And so that's why you get all of these weird dark matter-like things going on.
So we're attributing these sort of anomalies to dark matter. But if there's gravitational effects that are happening farther than we anticipated, then perhaps it's actually just
extra gravity. Essentially, yeah.
And this will come out with more Gaia research.
In terms of those binaries, it will. But this is just one axis of dark matter, right? Because there's also the question of like how large structure forms, like the actual cosmic web of the universe itself. There's how galaxies move. There's the spin of galaxies. There's dwarf galaxies that move around galaxies. So there's like many pieces of evidence that we can look at.
That farther gravity.
So binaries is just one snapshot. Right. But I think it is a really interesting snapshot because there we really don't expect much dark matter to be at play, because this thing is the size of a solar system. And when you get to scales of a solar system, there just isn't a lot of dark matter because it's very like diffuse. It's more like a very diffuse porous cloud of material that spans more or less the entire galaxy. So you really don't expect in any one solar system there to be much of it to be influencing things. That's why the planets in the solar system all follow Kepler's laws of gravity. They don't have any Mond behavior, right? There's no planets which orbit slower or faster than they should be. They all perfectly follow Newton's prediction. So on the solar system scales, we don't really expect either Newtonian gravity nor dark matter to be an issue. But for these wide binaries, they're like where planet 9 is kind of distance. Once you get out to that kind of separation, that's the starting point where you start to see deviations between what Einstein and Newton would think versus what Mond would say. So we'll see. It's going to be really interesting as we get more data. And I love it when there's a scientific debate. I think that's always fun. Like from the outside, it's not my field. So I just love, diving onto the Twitter and the debates that you see between scientists getting really riled up about it. And I think that's what makes science fun, is when people are passionate and they care about their ideas. But as long as, they're still dispassionate enough to be objective when the data goes against them.
Oh, wow. And then as far as telescopic research within your field, I believe a month ago, October, you and your team and your lab basically got access to Hubble.
No, James Webb.
Or James Webb, sorry.
Yeah.
And you were able to effectively, use the telescope to conduct exomoon research.
Yeah, I'm very excited about that. Yeah.
And you've collected the data.
Yeah, the data's down the ground. The observations went well. We observed for 60 hours, which is really like a lot of time on the James Webb. I mean, this is a $10 billion telescope. I think our observations account for like $30 million or something like out of how much telescope.
Crazy.
It's like a crazy amount of money for just staring at. And we just stared at one object for 60 hours. That's all we did. And we took one photo of that star every 1.6 seconds. So we have, I think, like a few 100,000 images of this star that we're poring over. And our job is to really just measure the brightness of that star. That's it, in each one of these photos, and see if we can see a little dip. First, I can tell you, we definitely see the planet. I mean, one thing we were worried about is, what if we schedule this at the wrong time? This planet that we're observing is a gas giant. It's very similar to Jupiter. Imagine Jupiter in your head. This is kind of the planet we're looking at. It goes around its star once every 1,087 days. So that's about 3 years. Mm-hmm. So only every 3 years do we get a chance to do this observation. So the observation came around in October. We caught the chance. And we were worried because it's a 60-hour window. What if we were slightly off in our calculations? Or what if the planet is wobbling or something? Maybe it might not even eclipse when we expect it to. There was no guarantee of that. So first off, we see, the first preview I can tell you is we see a giant signal of the planet. So when we first saw it, thank God.
We got a heartbeat.
We didn't screw this up. And then we see actually transits of the other planets in the system. There's actually 4 planets in the system. And we actually even see one of the other planets transit at the same time, just after, which is much, much smaller planet. It's a super Earth, but we can see it like this big, beautiful signal where that transits. So both of those, we have a crisp, clear signal on. And what we're trying to do now is to look for the exomoon in the data, if it has an exomoon. And that has been, it's really challenging work because we are pushing this telescope, even as impressive as James Webb is, we are pushing this telescope to its very limits to try and squeak out as much of the signal to noise as we can. But we believe in our original calculations we made for the telescope that we could detect Titan, which is around Saturn, Ganymede, which goes around Jupiter, and Callisto. Those 3 moons, which are real moons in the solar system, James Webb should be able to detect all 3 of those. If it has just one of them, we should see it. And this is, as I said, it is like as close to Jupiter as you can imagine for a planet. So it really should have some moons. If it doesn't have moons, that's pretty weird because we think all gas giants really should form them. And so, we're looking hard through the data to see if we can pull that signal out. And it's a lot of, at this point, we're in the phase of really like data massaging and data analysis. We're going like deep into every pixel. We're trying to correct for various wobbles of the spacecraft and thermal effects. So it's very much the black art of data science phase that we're in right now.
And it might be preemptive, but do you know when the paper, the research will be published?
I'm hoping within a year of the observations, because that's when our proprietary period runs out. So that means that the whole world gets access to our data.
Oh, wow.
October 2025. We get 1 year where just us get to look at it. So that's kind of like it's a good thing. There's a clock ticking that like get your ass in gear and like make sure you get your data out by then, because I'm sure lots of we know there was at least 2 other teams that proposed to do exactly the same thing as us, and we may have been more than that, in fact. So we know that there's definitely going to be competition breathing down our neck on this one.
Well, I'm so excited to see what the outcome is. I know it's too soon to tell, but I'm gonna say there's an exomoon. That's what I believe. Okay, knowing nothing other than
I believe you. There is an exomoon. The question is, can we detect the exomoon?
Yes.
Yes.
I believe.
In CoolWorlds.
We will revisit this in 1 year. But the first place that you're going to talk about this discovery, I know, is the CoolWorlds YouTube channel.
I'm sure we'll do a video on there. Yeah, absolutely. I'm looking forward to that one.
Yeah, which everybody should check out. It's absolutely amazing. And that's where you're going to find Dr. David Kipping all the time over at CoolWorlds or at Columbia. If you're a aspiring astronomer, astrophysicist, they can find you there.
Yeah.
Any other place people can find you if they want to keep up to date with the bleeding edge of?
Yeah, I'm on Twitter as David_Kipping. I recently moved over to Blue Sky, like so many academics. I'm on there as well. Just search for David Kipping, you'll find me on there. And then the other thing I do is that we have a podcast. It's much smaller than your podcast, Mark, but we have a little podcast called the CoolWorlds Podcast where I chat to other astronomers. We try and the last episode I think we did was recent episodes we've done have been sort of about the fate of the Earth. We talked about the black hole information paradox that we talked about today in depth. I kind of like it because I get to talk to like the person who is like really eating that field up day in, day out. But I tried to find people who are really good at speaking as well. So it's kind of a nice blend of those like champions of each field.
That's
so
awesome.
If you're into that, check out CoolWorlds Podcast.
Yeah, you get to feel like me sitting across a
Right.
genius of field, and you're like, oh my God, what do I say? But thank you so much for the time. This has been just immaculate. I really appreciate everything and for entertaining all my dumb questions.
They went dumb.
And furthermore, entertaining the questions of the audience and everyone that wrote in. I really appreciate everyone at home that was listening and everyone that will listen in the near future. We do these lives every week with very interesting and brilliant people. Typically not all of them with as charming of a smile as Dr. Kipping. But if you're interested in being a part of the convo, make sure you're tuning in live. Hit the notification bell so you know when we're going and you guys can tap in with your questions. Thank you so much for doing this. I really appreciate it. And I would love to do it again soon.
Yeah.
Amazing. Thank you guys so much for watching. Appreciate y'all. This has been another episode of Camp. All right. See you guys next time. So good.